Testing 1, 2, 3, 4, 5. Welcome to Two Horses, Day 2.
Hello, good morning. Before we start, a very quick announcement, which is maybe not particularly urgent, but for Thursday, the drinks that you have to pay for are only alcoholic drinks. Non-alcoholic drinks are free, but you have to pay in cash if you want to drink some alcoholic. So I'm saying this already now so you can try and find an ATM somewhere and get some cash. That's all. Google. Sorry. Yeah, I don't know.
Oh, this one here?
This is for upstairs.
Is this automatically on? Okay. Good morning, everyone. Did you have fun in Berlin last night? Yes? All right. Looking a little sleepy-eyed this morning, so that probably means you did have fun. So I have the pleasure of chairing this morning's session, but before we get started, we have 2 minutes left in the schedule. So I wanted to share with you an experiment that I did. Megan Bedell and I were talking last night about whether ChatGPT could make funny horse puns. I'll let you be the judge. Good morning, everyone. Welcome to the Two Horses Conference. I hope you're all ready to saddle up for a day of high-resolution discoveries. No. We're trotting into a fascinating day of spectroscopy. Let's ensure we don't rein in our curiosity. I'm still going. I love the bomb. Hold your horses, because today's sessions are sure to be a thoroughbred of astronomical knowledge. No. Okay. Everyone, you should thank me, because I have set the bar so low that you can improve upon ChatGPT. I'm not worried for our future. I think we'll all have jobs for the long run, at least in stand-up comedy, because ChatGPT is not cutting it. All right. Thank you for humoring me. That was, I think I amused myself more than any of you. That's great. So without further ado, I'd like to introduce our first speaker of this morning's session, Sid Gandhi. And yeah, take it away.
Okay. Oh, yeah. Cool. So I'm not going to even try and match the horse puns. It's just, I'm sorry, it's too much. But I will keep my hat on. So hi everyone. I'm Sid. I'm an assistant professor at the University of Warwick, and I'm going to talk to you today about atmospheric retrievals with high resolution. This talk is going to be split into two. So the first half, I'm going to go through the kind of three big things that we need to really worry about with high res. And then the second half is going into some of the nice things about high res and potentially some of their shortcomings for when we try and do retrievals. So a retrieval is basically just a fancy way of saying, I want to fit this spectrum, whether that be a low resolution spectrum or a high resolution spectrum. Typically for transiting planets in the infrared, you won't get a spectrum out quite like this. It'll often be that your planetary signal is buried somewhere in the noise. But generally what you have is a whole lot of free parameters that go into it, such as the chemical composition. You know, you can do this in two big ways. One of the ways is having a free retrieval. That's where the abundance of like water, CO2, methane are all free parameters, and you let them vary and do their own thing. Or you can have them potentially in a chemical equilibrium scenario where you couple the temperature and the overall carbon, oxygen, nitrogen content of the atmosphere and kind of just work out basically what the reaction rates are and what the equilibrium values for all the abundances are. And you may also have other things in your parameterization that you want to include in your model, like clouds. And when we're dealing with high res, we also want to worry about some velocity shifts as well. So some of the strengths and weaknesses of high res. So the strengths are like, you know, we're very sensitive to the trace species. we generally get very robust detections, and the reason for that is because at high resolution, you know, you're often looking at all of these kind of individual lines, and we often have many, many thousands of these lines for molecular species. So it means is that there's loads of these different places in the spectrum that we can kind of like latch onto. And it's very robust with abundance ratios. I'll come on to that. And because we're probing these line cores, which are generated at different altitudes, we can often be sensitive to a much wider range of altitudes in the atmosphere, a wider range of pressures. And we're also sensitive directly from the spectrum to 3D effects and atmospheric dynamics. However, we do lose some of the continuum information. You know, really the thing that we're really latching onto in these retrievals is the line cores, and we're not as sensitive to the absolute abundance values. And it can often be quite difficult in detecting telluric species because we have to look through our own atmosphere, and it can often also be difficult to extract the planetary signal effectively. So here is just a very simple diagram of what a retrieval does. Let's start with the atmospheric profile. Let's just assume something for the atmosphere, some abundance, some temperature profile, etc. We compute our model spectrum through use of the opacity of each of these species. Then we need to do something called model reprocessing, and then we compare that to our data to get a likelihood, basically. How well does my spectrum fit the data? And then you just kind of iterate over this loop through a Bayesian analysis, you know, MCMC, multinest, whatever you want, many, many millions of times until you get a convergence, basically. So I'm going to talk about these three things in a bit more detail. Let's just focus on the opacities and the line lists. Because we have a high-resolution spectrum, we're going to have to make sure that our line lists are accurate enough for that, because if we have, say, a resolution of 100,000, then we have to make sure that our lines are positioned in the right places so that we're able to effectively kind of pull out the signal. We also need to make sure that we have really accurate pressure broadening coefficients so that we can correctly model the line profile. If your line is, for instance, under-broadened, then what might happen is that because the data has slightly more broadening than the model will expect, it might try and push the photosphere of the atmosphere down in the atmosphere at higher pressures, and that can obviously change your abundance values. So just having the pressure broadening coefficients wrong might suddenly mean that your abundance estimates everything just kind of gets pushed down into the atmosphere. So it's really, really important that we get these right. But thanks to the hard work in the last few years of groups like ExoMol and HiTemp, we now have a whole range of high-resolution line lists for a range of molecular species, whether that be oxygen-rich species, carbon, nitrogen-rich species. We've also got H2S, SO2, and refractory species. In fact, the VO line list came out just recently. And these are all applicable to these very high temperatures and very high resolutions because they've all been experimentally verified as well. So there's been a lot of work that's happened. And we're even getting some line lists now for secondary isotopologues, so for things like 13CO and H218O as well. But I'd say that we probably need a little bit more work on the hydrogen and helium pressure broadening coefficient as well, just to make sure that we are as accurate as we can be. But just in the last 5-6 years, we've seen massive progress. And I'd say we're in pretty good shape, actually, for most of the relevant species that we want to look at. So the second thing that I want to just explore is something known as model reprocessing and the data analysis. Now, this is probably the most relevant for if you're doing transiting planets in the infrared, because that is where your planetary signal is often just completely buried in the stellar signal, in the telluric absorption. And during your transit, during your observation, you may also have air mass variations. And if you're looking at the L and the M bands, you might also need to worry about the thermal background. So your planetary signal is absolutely tiny in all this. and you have to clean it out. And you have to clean it out potentially using these principal component analysis or singular value decomposition algorithms. And you can see the effect of that here. So step 2 from Brogian line 2019, you can see is the clean model. And then you put that into the data, and then you simulate that data set, and then you apply that PCA, and what you actually end up with is something from step 7. And you can clearly see that that is just completely different to what you started off with. First of all, these sharp lines are now kind of a bit more blurred and a bit more smeared out because the PCA has actually removed some of your planetary signal. And you also have these kind of artifacts kind of going the other way. So it's really important that we do this to our model as well. So the way that we've used to clean up the data, we have to do exactly the same thing to the model, just so we're doing a like-for-like comparison. So yeah, this is really important, because otherwise you'll significantly bias your results. And finally, we come into the likelihood. So how do we actually compare the data, the analyzed data, and the reprocessed model? Well, the easiest way to get a detection is through something known as cross-correlation. That's where you basically just slide your model along, and where you get that peak in the velocity is where you get a detection. Now, for this, it's a little bit easier because you don't have to have the perfect temperature profile. You don't have to have the perfect abundance for these species. Because you have so many lines to go at, you can often find a good detection. Obviously, it will improve the better your fit is, but you can often get a detection with cross-correlation quite easily. But we want to be a little bit more quantitative, and we want to penalize bad models, and we want to make sure that we are able to constrain these. And there's various methods we can do. Two of the big ones are the Brogian line method and the Gibson method, which allow us to really explore in detail through things like the variance of those models, how well they fit the data. Sometimes for these, you will need to have extra retrieval parameters, like this alpha and this beta parameter here, which are like scaling factors that you have to retrieve. And you can also use them as a good guide, because if you get a result, for instance, in your model scaling factor that's roughly close to 1, then that means that, like, well, this model is a pretty good fit. If you're getting that suddenly I need to scale my model by a factor of 10 in order to fit the data, then it might tell you that, like, actually there's something going on here. And these methods allow for uncertainty terms, the noisy parts of the spectrum, to be penalized as well, which is really nice. Just a brief mention about the computational resources that you need. Obviously, if you're trying to compute a very high spectral resolution model with any number of species, in the optical, we've seen that we can get 10, 15 species at a time sometimes. So for that, you need a huge amount of memory. You typically also need to over-model your data. So if your resolution of the data is R of 100,000, you typically want to generate your models at R of 200, maybe even 300,000. When I was working with espresso data, I generated models at R of 500,000, and yeah, the CPUs were not happy at that. And obviously, for each one of these wavelength points that you have, you're going to have to compute the opacity of every single one of your species to work out the optical depth and the spectrum. You can also include other parameters, such as modding correlated noise, Gaussian processes, and so that can, as well as having a high memory and a high CPU usage, now you also have a very high dimensionality of your problem. So it can be very challenging to do. And so it's really important that that you're able to be as computationally efficient as you can, but also that you probably need an HPC or GPU if you don't want to sit around for a month waiting for it to finish. And there's definitely, I think, a need for machine learning tools here, even if it is just to identify the species that we put into our Bayesian analysis. So that was basically like the ins and outs of retrievals. I'm going to go into more kind of the advantages and disadvantages now for the second half of my talk. So first of all, with cloudy atmospheres, I think this is where high-resolution observations actually have an advantage. So if we're looking at a transiting planet, if we have a cloud deck, basically it'll just slice your spectrum off from the bottom. But you can see that because these line cores are generated at much higher altitudes, these lines for these species do kind of still stick up above the cloud layer, so we can still kind of go at them. This is a little bit more difficult, and you will have a much lower signal, and sometimes, you know, in this case for water, telluric absorption might mean that it's difficult to do. But it's still possible. As for detecting cloud species themselves through the actual variation in the scattering and of the opacity, I think that's going to be more difficult because you're going to have to go at them kind of indirectly, because you have to basically see how do my line features for these species like water, CO change as a function of wavelength to try and get the cloud feature. So it is doable, but you will have to be a bit kind of careful with how you do it, and it will be quite hard. For direct imaging, we've actually been able to get direct constraints on the cloud decks. Very recently is a paper by Jerry Schwan, where you can see there's a very nice constraint of a cloud deck at 10 to the minus 1 bar. And what's really nice about this is that it also coincides with the condensation curves with iron and magnesium silicate. So it tells us that, you know, we are along the right lines, and we can definitely constrain these given the higher signal to noise that we have for direct imaging observations. So that's really good. What's really bad, though, is tellurics, especially in the infrared. They kind of, you know, they will kill your signal, and the maximum peaks for where all of your water absorption is also, annoyingly, where the maximum peak of your telluric absorption is. So you can't really look at those wavelengths to find water. And actually, water can be very difficult to constrain. So here I'm showing two works that looked at tau bu, and for one of them there was really no constraint on the water. Like, it just said, you know, there is no water in this atmosphere. And then another work showed that is there, but there is a velocity shift. So this might tell us that, you know, detecting species like water, CO2, methane is going to be really challenging, and perhaps we need to fit the tellurics simultaneously or in some kind of pre-retrieval step in order to make sure that it is matched as effectively as possible. But one of the places where I think we're going to do really well is in abundance ratios. So because of the way that high-resolution spectra work, if you have two species with two features at two different wavelengths, if you kind of like increase the abundance of one and increase the abundance of the other sort of together and sort of make the continuum kind of come with you on that, then the spectrum will look fairly similar. So while you're not very sensitive to, say, the abundance itself, the volume mixing ratio for species, when we look at the ratios, suddenly those posteriors kind of shrink. So when we want to look at, say, C2O ratios, that might actually be quite robust if we're doing ratios of species, but doing metallicity might be more challenging. So perhaps we can find a way of changing the metallicity from like a sum of all the species to like a ratio, for instance, the CO2 to CO ratio, because the CO2 is a lot more sensitive to the metallicity of the atmosphere. So that might be a way to go to make it a bit more robust. We can also get constraints on the different isotopes. So for various species, we can get these constraints for the primary isotope, which is the most common type of, 12 carbon is the most common, 16 oxygen is the most common, but 13 carbon is roughly 100 times less abundant. And because of the nature of the high resolution observations and because of the fact that you have a heavier atom in the carbon, it means that all of these lines are kind of shifted. And that means that we can really go after them at high resolution. And we can constrain these not just in directly imaged planets, but also in transiting planets and compare, what they are to formation scenarios. We're also able to get constraints on the 14 to 15 nitrogen abundances as well as oxygen as well. So in the last like just 3-4 years, this whole field has absolutely exploded, and I think this is going to be really, really important going forwards. I should also note that in the optical, we have detected a vast swathe of species, mostly atoms, in ultra-hot Jupiters, both neutral and ionized, and it's because these ultra-hot Jupiters are just so hot that basically everything is a gas. And I mean, they're detecting species that I barely know from the periodic table, and like pretty much everything that you see here has all been detected, and even its ionized form, which just shows you how sensitive we are to all of these. And I think that this is going to be really important in the next few years, because we want to really understand the refractory content of these planets. It will obviously be a lot more difficult for the cooler planets because they're just not gaseous in the atmosphere. But certainly for ultra-hot planets, we can definitely go after these. And as much as I hate to say it, atmospheres are three-dimensional. I like it when they're just like a slab that you can just model nice and easily. And we are directly sensitive to these 3D effects in the atmosphere. You can see here that the constraints that you get for one half of the terminator compared to the other half of the terminator on this side, you can just see that the posteriors don't quite match. They're different, and the reason for that is because you have these circulation patterns that will often blow material from the hotter side to one of the terminators, then it will go over to the cooler night side, then as it comes around to the other terminator, it will have a different temperature, and there may have been reactions and changes in the atmospheric structure that has happened, the composition has changed, and we are directly sensitive to this because we can actually just resolve it spectrally. And as we saw yesterday from Lisa Nortman's talk as well, we can get different constraints on not just the very, very hottest planets, but also pushing down towards, sub 1500 Kelvin, which is really exciting. We can constrain differences in the temperature and in the composition, which is nice. We can also directly constrain the atmospheric dynamics, and by that I mean like the winds of the atmosphere, whether they be circulating kind of around the equator in a belt, whether that be an outflow from the planet, or whether that be a day to night wind. We are directly sensitive to this just because of the very high resolution of the observations, and because we have so many lines to go at often, it can be a very powerful tool. I would say that because cooler planets will typically have much lower wind speeds, this might make this more challenging. But it's not impossible by any means. I think in the next few years, direct imaging, especially for isolated targets like brown dwarfs, is going to be really, really amazing, because you see here the panchromatic spectrum that we got from JWST for VHS 1256. It's absolutely incredible that this is all just the data. It feels like, I don't even think my model could get down to that higher an accuracy. So it's amazing that we see that. And we're able to constrain patchy clouds. And I think just yesterday there was a paper looking at the weather and the actual variability in these brown dwarf atmospheres. And with these like 8-meter class telescopes that we have, and with these very high signal to noise that we can get for these brown dwarfs, I think we're going to see a lot of progress here for understanding, the fine detail of these. And through direct imaging, we're also able to get good constraints on companions. Here I'm showing constraints that we've got for water and CO in Beta Pictoris B, and in the L and M bands, we're also able to get silicon oxide as well, so there's potential science for that, which is really exciting, that we're able to get good constraints on these directly imaged planets as well. And in the next few years, we'll really be able to kind of hone down and get all of these constraints and compare them to the hot Jupiters, so that we can determine, do these planets form in a similar way? Do they have a similar composition? If not, why not? So that's really exciting. But I think what's I think probably the most exciting is being able to combine high and low resolution. Now, you can combine them in various ways. You can just say, I want to do infrared high resolution and infrared low resolution, so you get the same wavelength coverage. And that can help refine your abundances and make them more robust and make sure that what you are seeing in both is consistent. Or we can do the opposite, where we do high resolution, for instance, from the ground, and we do infrared from space. And that can help us to get the refractory to volatile content. And the refractory to volatile content gives us a good measure for the amount of solids that were accreted from this planet as it formed. And you can also just see the constraints that we get much better for the temperature profile for the atmosphere as well. So low resolution, you're doing really well at the photospheric temperatures, but then it kind of just spreads out away from that. Whereas at high res, they all seem to kind of be parallel, and that's because the thing you're most sensitive to is temperature gradients. And so then combining the two, you kind of pin the photosphere temperature, and you get these photospheric gradient constraints, which can help you really refine the temperature profile really nicely. So I think we're in for a lot of really high accuracy constraints in the next few years through this. And let's not forget that the ELT is really not that far away. We're going to have Metis, we're going to have Andes, and that's going to revolutionize not just transiting, but also directly imaged planets. Just the amount of science you can do with a 40-meter telescope will mean that we can really explore in fine detail all of these different 3D effects, can look for these trace species in these larger planets, and push down towards these cooler, rocky planets. But I would say for cool transiting planets, their lack of strong orbital velocity might end up being a bit of a problem here, because the PCA often removes components that are almost vertical. So if there's not much of a Doppler shift from this planet, your PCA might be a bit too aggressive and just completely clean out your planet signal. So we're just going to have to, be careful of that. And looking towards the future, as we start putting down towards more Earth-like planets, we will start looking towards biosignatures. Don't ask me which biosignatures. I'm staying out of that. I'm gonna say that, as all good physics textbooks say, this is left as a trivial exercise for the reader. But I think, given the nature of the high-resolution observations, we should be quite robust, because we often have many thousands of lines to go at for each of these species. So if you could find a biosignature gas, then I think high resolution would have a role to play in detecting that. And I think also for the lower temperatures, the line lists and the experimental accuracy that we can get is also much easier. So we can use something like HYTRAN, which does make it all a bit easier to manage. I think the hard part is going to be distinguishing between telluric absorption and exoplanetary signals. So, if we find a biosignature, can we be really sure that we're not just seeing the biosignature as some artifact from the Earth's atmosphere, and just being sure, yes, that's definitely from the planet and not from us. So, yeah, I'll just leave up my conclusions and say thanks for listening and open up the questions.
Plenty of time for questions. And next up, we have Peter Smith, who will be talking about Stronger Together, expanding atmospheric inference capabilities by combining ground-based and JWST spectra. So I'll give you a sign at 10 minutes in.
All right, howdy folks. My name is Peter Smith. I am a PhD candidate at Arizona State University, and I'm happy to tell you about some work I've done that is now published, so you can follow along to the paper if you want. There's a QR code. So one of our major science goals of like why we're here in the first place and studying exoplanet atmospheres is to try to figure out how do planets form. And there's many different predictions of how a planet formed, where it initially formed, when it migrated, how that impacts the final atmospheric composition. And so our main goal is to take lots of measurements of elemental enrichments and ratios and fill out some kind of plot like this where we have lots of predictions and kind of place a planet into context. And this is going to require, for example, if you want to measure the volatile content, good measurements of both carbon and oxygen and maybe some other elements as well. And of course, the way we do this is spectroscopy. So here's a little cartoon spectrum. We have the continuum and then some absorption lines. And these line contrasts are going to be driven by mainly two things: the abundance of that particular gas and the slope of the pressure temperature profile. And so when we do spectroscopy, we want to know the things that determine the shape of it, which are the vertical thermal structure and the composition. So you can do this with low res, and the process is a little bit different than what we do. So say you want to measure the thermal emission of a planet, you'd measure the light curve as it passes behind the star, and the difference between in eclipse and out of eclipse is basically how bright or how hot the planet is. If you do this in multiple wavelength channels, you can kind of create an eclipse depth or some kind of brightness temperature spectrum, and you can see, okay, at what wavelengths are different molecules and gases contributing to your spectrum. And then you can move on to your Bayesian inference or your retrieval like we just talked about. Back to this cartoon spectrum, if this is the true spectrum that went into your instrument, your data product looks something like this. It's been binned down, you have less detail, especially you don't have as much vertical resolution for those lines, but you have a very good idea on where the underlying continuum is. High res, I don't need to talk much about this with this crowd. We do the whole time series, you do your cross correlation map, and for a while our main data product was these kind of cross-correlation maps where we do different test values of the semi-amplitude of the planet's orbit and then any systemic velocity. So you get something like that. And then you can also move on to your retrieval. So back again to the cartoon spectrum. After this thing has gone through your instrument and you've done your detrending, you really can't see anything. But through cross-correlation or through our likelihood mappings, we can kind of work out some kind of idea of the underlying planet signal. And like Sid was mentioning, we're very sensitive to individual line ratios, and also we're sensitive to individual line shapes, which is very useful, those two things, for measuring the composition and also dynamics. So we have to make a choice, potentially, when we want to do spectroscopy of our exoplanets from space. We obviously don't have to worry about the Earth's atmosphere, but we are, though, at low spectral resolution, but we get that continuum. From the ground, sadly, we have to deal with the pesky air that we breathe. We're at high spectral resolution, which is nice, but the continuum, what happened to it, is it there, who's to say? So our intuition then would be that if you really care about the thermal structure of a planet, you may want to go at low res, and if you really care about the composition, maybe go high res. Well, I'm very bad at making decisions, so I decided to just do them both. They have complementary information, so just do them both. So I did this for WASP-77 WASP-189b, a fun hot Jupiter. It had both IGRINS data and near-spec data. And so this is a fun planet. So previously Mike showed that, yes, we can do like good science with high res with IGRINS as well. Measure the PT profile, nice compositions. It was a little bit weird that it was a low metallicity, but later with JWST we did confirm that low metallicity. You can kind of do a retrieve by eye, and you look at the CO2 feature or where it should be, and it's not there. So you can say, oh yeah, low metallicity, no retrieval needed. But I also have some new data. So Mike's previous paper, we had pre-eclipse observations, also new post-eclipse observations with IGRINS, and we're going to combine this with the near-spec data and see, basically, can we confirm this intuition that the low-res data will be good for composition and the high-res for, or I mixed that up. Low-res good for PT profile, high-res good for composition. So already before doing the combined analysis, the two data types predict each other pretty well. So what I'm showing here is after doing a retrieval on the IGRINS data alone, post-process some models from the posterior out to the near-spec wavelength ranges, and it's pretty consistent with the near-spec data already. Blue points are where it disagrees the most, and I'll talk about that in a second, but it's within the spread of the posteriors, it agrees pretty well. And also, if you take the near-spec best fit model and divide that out of the IGRINS data, do a cross-correlation map again, there's only residual noise. So that also indicates that the near-spec data agrees with the IGRINS data. Combining them, so individually here I'm showing some posteriors of interest, so abundance of water, CO, and then kind of a volatile enrichment or metallicity proxy in the C to O ratio. Basically, if you don't work a lot with posteriors, a narrow histogram is better. And then here's some PT profile draws where the line is the median, and then the shaded region is like 1 sigma confidence. So IGRINS already, we can see very good constraints on the abundances. PT profile, it's there, a little bit of a spread. Looking at near spec, one thing to see though immediately is that the histograms are basically right on top of each other. So they are consistent, they agree, which is very, very nice. It means somebody's doing something right. You will notice that the abundance information is a little bit less well-constrained compared to IGRINS, which is what we expected, but the PT profile is also very nicely, we're more confident about it and in more pressures. And then when you combine the two, you leverage both of these strengths, and our constraints on the abundances are a little bit better, and the constraints on the PT profile are a little bit better. So by combining them, we've actually gotten a little bit more inference power. What exactly is happening, and to explain this, this is the photosphere of the best fit model. So this gray line is basically at what pressures we're seeing at different wavelengths. And I want to highlight in this kind of lower pressure regime where IGRINS flares up in its confidence on the shape of the PT profile, that's where it's not sensitive to. So IGRINS is mostly sensitive to about 1.5 to 2.5 microns, whereas near spec is from like 3 to 5-ish, and it probes a lot lower pressures. And that's why near spec is so much more confident in those pressures. And so by decreasing our uncertainty in the low pressures, we're able to decrease that degeneracy between gas abundances and the shape of the PT profile, and that propagated back to just an overall decreased uncertainty in the composition. And I want to highlight that this isn't just an effect of just having different wavelength coverage. So remember this region here where the IGRINS posterior draws didn't quite agree with the near spec data. You'll notice that here, that around like 4 microns or so, these are pressures where IGRINS probes as well. And you can see it's a little bit below 1 bar, 100 millibar. Thanks. And IGRINS is very confident there, but as we can see here, it's not quite as accurate as you would presume from the near spec data alone. So indeed, the low-res data from NearSpec is more accurate when it comes to inferring your PT profile. But of course, when we combine them, the fit is beautiful. Back to this, this diagram of the oxygen and carbon inventories. Before the launch of JWST, we had, of course, Jupiter from Juno, and then we had a couple of these combined high-res, low-res studies before. We had Tau. Then shortly after the launch of JWST, we had a couple of more of such measurements, and WASP-77 sits right there. Very, very nice precision and comparable to what we can do with Jupiter, which is very exciting. This plot is out of date. I encourage everybody to check out Megan's paper. She has this nice table with a lot more of these measurements that have been made in the last year. It's been a busy year. In the future, I think we're not just limited to just PT profile abundances. We can start to really figure out the 3D effects, the climates of these planets. So like at low res, we do a lot of phase curves, eclipse mapping, to kind of figure out the longitudinal brightness or temperature distribution of these planets. And of course, at high res, we're sensitive to wind speeds, the line shapes, the line contrasts. And of course, these things aren't independent. The dynamics, the wind speeds, they are all physically interlinked. So by measuring one and the other at the same time will really help us nail down the three-dimensional global climates of planets. And of course, so right now we're doing great with high-res, with the hot Jupiters, the ultra-hot Jupiters, but of course, for cooler planets, space-based spectroscopy has definitely an advantage. Once the ELTs come online, ELT, GMT, we will have a lot better capabilities to kind of look at these cooler planets. And so for the planets that are accessible, we might actually be still comparable in terms of neck and neck of like space-based, ground-based, measuring the compositions and other atmospheric structure stuff. I'll leave my summaries up here. Basically, don't limit yourself to just space, to just ground. They're both great. They'll both help each other. We can all be friends with the JWST people down the hall at our office. It's okay. Thank you.
Fabio Lesjak, who will be talking again about an ultra-hot Jupiter, this one WASP-189b. I'll give you a 10-minute warning.
Okay, thank you. All right, hi everyone. Yeah, I'm Fabio from the University of Göttingen, and I'm going to talk about our CRIRES Plus observations with WASP-189b. Yeah, so WASP-189b is maybe kind of famous for being one of the hottest exoplanets out there, and there's already a vast library of different species that have been discovered in its atmosphere, mainly in the visible. And in addition, so if we look into the literature, we see that there's some kind of velocity offsets in transmission and emission observations. So here on the left side, you see the iron signal in the transmission spectrum, and there we have a blue shift of a few kilometers per second. And then on the other side, there's the emission observations. And then in the CO signal there, we have a redshift. It's a bit hard to see on this figure, but it's around 5 kilometers per second shifted to the right. And well, what's one possible explanation? Typically, what people use to explain this away kind of is the day-to-night side wind. So if we look at the viewing geometry, on the left side in transmission, the hot material from the day side streams to the night side, and then the material comes towards the observer, inducing a blue shift. And on the other side, in the emission observations, the material is going away from the observer and therefore inducing a redshift. And so this is one way to explain these varying shifts in the observations. Yeah, so we observed WASP-189b with CRIRES Plus shortly after the secondary eclipse, so observing the day side with a resolution of around 140,000. And we used the observation in the spectral K-band, which covers many lines of interesting species in the atmosphere, most notably CO and iron, but also some more molecules like water, CO2, or iron hydride. And then first step, of course, is the typical cross-correlation analysis. And here you can see the planetary trails of CO, I think, quite clearly. And if you squint really hard, you can maybe also see it for iron. And then, of course, if we do the KP-Visys analysis, all of the signal combines and we get a nice detection of these two species. And again, we see here there's a redshift of our signal compared to the expected position of around 5 kilometers per second, so that's quite consistent with the previous observations. And all the other molecules, or in general species that we looked for, we didn't find anything else. For most of these molecules, at least, that's not really surprising because the day side has a temperature well above 3 or even 4,000 Kelvin, so most of these molecules are probably dissociated. And then the next step is a retrieval using an MCMC sampler. And then I first want to go a bit into the chemistry, what we found there. First of all, the TP profile is inverted. That's not really surprising. And we already saw this in previous observations. And then we got some constraints on the abundances of the two detected species, CO and iron. And we also tried to constrain the C/O ratio and metallicity. For this, we basically assume equilibrium chemistry. And then because we only have these two species, we kind of have to make a few more assumptions to get some constraints. So basically, we assume that the abundance of iron is a good proxy of the metallicity. And for the C/O ratio, we assume that the oxygen content also scales with the metallicity. And then we can determine the carbon content from the CO abundance. And under these assumptions, we retrieve a C/O ratio of around 0.3, so quite subsolar. And the metallicity is supersolar, around 1.9. But you see that the distribution is quite broad. I mean, with only these two species, it's a bit difficult to constrain the chemistry. And also there's some degeneracy between these two parameters. Right, that's nice. So chemistry, okay. But what about the winds? So we ran a second retrieval where we implemented a wind model which is a bit more complex than what we used before. So here the idea is basically that we first do a 2D model of our day site and see what kind of velocities we have there, assuming different wind parameters, and then we calculate a line profile from this, and then convolve our model during the retrieval with this line profile. And the two wind structures that we looked at is first the day-to-night side wind, which we parameterize with just a single velocity. And you see here, as the velocity increases and decreases, this changes the resulting line profile with a redshift, but also a significant line broadening. And then the jet, equatorial jet, is determined by two parameters, a jet velocity and a jet width. And the effect of these two, or in general of the jet, is mostly broadening of the lines, and especially in the wings of the lines, we get more signal there. And then, of course, we also have to include a tidally locked rotation. This planet is really close into its star, so it's basically a safe bet that this is tidally locked. So here, starting with the velocity distribution of a tidally locked rotation, we add up all of these different effects to get a vast range of different line profiles that could be present in the atmosphere. And then the idea is basically we have these three free parameters in our retrieval, and then we calculate the line profile, convolve this with our models, and in this way we try to constrain the different wind parameters. Right, so this is the model, and these are the results. So in the right side, you see our best fitting line profile there and the corresponding velocity distribution. And basically, our data fits best to just a day-to-night side wind of around 4.5 kilometers per second. And as you can see in the posterior distributions, the jet velocity is basically consistent with 0. So at least in our data, we don't see evidence for jet. And if there's no jet, we can't really constrain the width. So therefore, the width parameter takes up all the parameter space. Right, so this is a velocity distribution that seems to be best fitting to our data. And then going back to our initial question about the offsets, can we actually explain this 5 kilometer offset with this wind distribution? So initially, without assuming any fancy winds, we had this offset of around 5 kilometers per second. And then with our wind model, this can be decreased to around 2 kilometers per second, but still a slight offset remains. So we can't explain away everything. You might ask yourself, okay, why don't you just crank up the wind speed even more? You can get rid of the redshift. But this day-to-night side wind also causes the line broadening, and therefore, I guess this strong line broadening wouldn't be consistent with our data, so we're kind of limited of how strong the wind speed of this day-to-night side wind can be. And other possible explanations for this remaining offset could either be an uncertainty in the system velocity. So the host star is an A-type star, which means that it's quite difficult to get a good constraint on the system velocity. So it might be that there's an uncertainty of, I don't know, a kilometer per second or something. Then also there could be a slight eccentricity in the orbit, a really tiny one, which would still be consistent with the trace that we see in the CCF map. And this could also be like a cause for a shift of around a kilometer per second. And then, of course, in our model, we didn't really include any hotspot yet, so it's a fairly simplified model. And of course, if we have a hotspot, and maybe this is even offset set to one side, this could change the different contributions of the velocities. So this could also explain this effect. Right, and to summarize, basically, we observed the observed line profile from our observation fits best to a day-to-night side wind of around 4 kilometers per second. And we don't see any evidence for an equatorial jet. And in the chemistry department, we calculate or we retrieve the high metallicity and the subsolar C/R ratio. And in general, these fast day-to-night side winds, they do cause a strong broadening. So it might be a bit difficult to just explain away any large offsets that you see in the data just with these day-to-night side winds. And you might need to invoke a bit more complicated physical processes with this. Right, and as the last point, I want to mention that I'm finishing up my PhD in winter, so I'm looking for job positions in spring. Thank you very much.
And wrapping up our mini session on ultra-hot Jupiters will be Marshall Johnson.
Yes. Thanks. All right. Hi, everyone. While I am Marshall Johnson from Ohio State University, while I'm afraid I don't have any horses in my talk, I do stick on a related theme with pairs of animals. So this survey that I'm introducing today is named PIRANGA. I am an avid birder, so I named the survey after which is a genus of brightly colored American songbirds, and our logo depicts 2 of these species. Turning to astronomy, though, the name of the survey is a only slightly tortured acronym for PEPSI Investigation, Retrieval, and Analysis of Numerous Giant Atmospheres. So this is a survey that we're conducting of roughly a half dozen ultra-hot Jupiters, obtaining both transmission and emission spectroscopy. We're using the PEPSI spectrograph, which was built just down the road from here in Potsdam, on the Large Binocular Telescope in Arizona. This delivers R of 130,000 optical spectra, and thanks to LBT's 2 by 8.4 meter aperture, we can get very high signal-to-noise, high-resolution spectra. I'll talk a little bit more about the goals of the survey in a minute, but we're looking at primarily at the atmospheric dynamics and structure of these planets, and I won't talk about it today, but we're also looking at the spin orbit angles and precession. Feel free to ask me about that afterwards. And this is a successor to the PEPSI Exoplanet Transit Survey, or PETS. I wanted to briefly introduce our team. In particular, I'm lucky to work with a number of talented students on this project. I particularly want to highlight Anusha Pai-Asnadkar, who will be on the postdoc job market this fall, as well as my undergrad students, Sydney Petz and Calder Lenhart, both of whom will be applying to grad school in the fall. So please keep an eye out for their applications. So in terms of the goals of this survey, there's a lot of things we can do with these high resolution spectra, which we've been hearing about over the past day, and many of these methods were put together by folks here in this room. From the transmission spectra, we can do things like looking at the changes over the course of the transit to probe the dawn versus dusk terminators. Using both the transmission and the emission spectra, we can look of different species. We can look at the wind velocities at different altitudes, look at different species line profiles to potentially look at the distributions of those species over the planetary photosphere in emission, look for changes in the strength or velocity of the planetary cross-correlation functions as a function of phase, which can also constrain the structure of the planetary atmosphere. And even just looking to see whether the planetary emission spectrum has emission versus absorption lines. It tells you about the slope of the temperature pressure profile of the planetary atmosphere. In particular, emission lines indicate a inverted temperature pressure profile, whereas absorption lines indicate a monotonically decreasing temperature pressure profile. We now have emission spectra of basically all of our targets, all of which show strong iron 1 signals in emission. I particularly want to highlight these 2 planets in the middle, TOI 1518b and TOI 1431b. We are presenting emission spectra of these planets for the first time, and our paper including these planets just went up on arXiv today. In this paper, we, in addition to the iron emission detections for these planets, we start to go into a population analysis of the presence of temperature inversions in hot Jupiters. So in this plot, we're showing as a function of the planetary equilibrium temperature on the x-axis versus surface gravity on the y-axis, the population of planets with emission spectroscopy sensitive to the presence of inversions. Many of these measurements have been performed by you here in the room, and we color code planets with inverted atmospheres in red, non-inverted atmospheres in blue, and then purple are isothermal atmospheres. It's apparent that there are a number of populations here for the ultra-hot hot Jupiters. Everyone that we have observed has a temperature inversion. We do not see any temperature inversion for the cooler hot Jupiters. There's a transition region in between with some isothermal atmospheres. The picture is less clear for these few high gravity objects where we have a couple of ultra hot high gravity objects lacking thermal inversions, but there's one object with intermediate properties between the other two which does have an inversion. So in order to do just a very simple comparison, we do a comparison to a recent suite of global circulation models by Roth et al. What I'm showing here, it does not cover the full parameter space covered by the data, but in the parameter space that does cover, these contours show the basically the slope of the temperature pressure profile in the region of the atmosphere that these observations are probing. The black dashed line indicates a isothermal profile. To the left are more and more strongly decreasing profiles. To the right are more and more strongly increasing profiles. Overall, these models appear to get the pattern more or less correct. The isothermal line is maybe a couple of hundred Kelvin too high, but it's overall a reasonable match to these data. One important point, though, is that that this is a model suite which does not include titanium oxide, which is often often proposed to be the cause of these inversions. The Roth et al. Titanium oxide suite provides a very poor match to the population data predicting predicting strong inversions for cooler planets where they're not observed. This, together with the, as we heard a bit about yesterday, the controversial searches for titanium oxide in these planets and lack of detections, although there may possibly be line list issues. Together with the strong and ubiquitous neutral iron emission from these planets, we suggest may indicate that it may actually be neutral iron serving as the primary agent of these, causing these inversions rather than titanium oxide. So shifting gears a bit, we're also doing a lot of work with our transmission spectroscopy during the transits, and in particular doing phase resolved analyses of the velocities during the transit. So this is some work from my undergrad, Calder Lenhart. This is showing for one planet the velocities as a function of phase during the transit, time increasing from bottom to top of iron 1 and iron 2. While we're still working on the interpretation of this, we do see both a distinct offset between the iron 1 and iron 2 absorption, as well as different patterns in the velocity as a function of phase for these two species. Comparing both of this as well as another planet that Anusha Pai Asandkar is working on, these actually show opposite patterns in the iron 2 absorption. The cooler planet on the left shows over the course of the transit, the iron 2 signal becomes more redshifted and decreases in strength, whereas for the hotter planet, the iron 2 signal becomes more blue shifted and increases in strength. This latter pattern is what has been seen in a few other planets, including WASP-76, whereas this pattern on the left has not been seen before. So again, these are brand new results. We're still working on the interpretation, but I think this highlights that we're really at the point of doing comparative planetology with these data. And we also have a third planet that grad student Connor Basinger is working on that we'll be able to add to these soon. So in conclusion, we're conducting a survey of ultra-hot Jupiter atmospheres in both emission and transmission with a PEPSI spectrograph, focusing on the structure, dynamics, chemistry, and also eventually the time variability of these atmospheres. Our first result from this survey is that atmospheric inversions appear to be ubiquitous among ultra-hot Jupiters, and it's possible that iron 1 is the primary optical capacity source and driver of these inversions. We're getting phase-resolved planetary velocities during the transits with which we can start probe the atmospheric structure of these planets. Multiple targets soon allow for comparative planetology, and we have several papers in prep, which hopefully will be out soon. Finally, I just wanted to highlight that in addition to PEPSI, next year we'll also have the iLocator infrared spectrograph going on the LBT, which will expand our reach into the near infrared. And I'll just leave you with a QR code to our new paper. Thank you very much.
So the topic is something about stellar atmospheres, and I picked up out a number of topics that I think are relevant for studying exoplanets and doing high resolution, high precision stellar observations. So of course it's not any extensive review. Let's start with something that is probably rather well known, convective line shifts. This is a fraction of the solar surface. As you know, there are many granules. There are many granules here. Actually, we could even run a quiz here. How many do you think there are? No, I don't know. But it's an image. So what is bright is hot. So the granules are hot. And this thing is not an image. It is a Dopplergram. It is a map in darkness space of the velocity shifts made with an instrument that measures the Doppler shift in some particular line. So the granules here are dark, not because they are dark as such, but because they're rising. Okay, these things are reasonably well known, but let's look at some properties that are maybe less obvious. How does granulation change with height? We have on the right side here the vertical velocity, which is here at the lower levels, and we go higher up in the atmosphere. Basically, it doesn't change very much. Things get more diffuse, things get spread out. To the left here, we have the temperature structure. This is what we saw in the previous image, and this is where the corresponding velocities are. We go slightly up in the atmosphere, and things reverse. Things become inverted. What was the bright granule down here is now the dark granule up here. The granules are now dark and rising. The intergranule lanes are hot and sinking. So the actual convective flux of these layers is going into the star, which may sound rather counterintuitive and sort of non-obvious. You can observe this if you observe images, take images of the sun, for example, in the continuum to the left here, or in the wings of a strong line that is formed high up, where you see the inversion. So what is happening here? Well, gases are rising up in the atmosphere. They reach a level where they become transparent and they lose energy by radiation. And they expand and they cool off. But that is one process. There is another competing process, and that is heating them by radiation coming from below. So you have the full flux of the sun or the star coming from below and heating the gases. And they will heat things up there. For example, the granular flows are going down. They're being heated from below. How efficiently they're heated will depend on the metallicity of the star. If the star has normal metallicity, there are many spectral lines, and these will absorb the light and thus heat the gas. If the star is metal poor, there will not be many lines, and there will not be much to absorb, so radiation will go straight through. And that is a main reason why the upper layers of stellar atmospheres are much cooler for metal-poor stars when modeled in three-dimensional modeling rather than in classical sense. Of course, the total convective flux going into the star is tiny compared to the total flux, but it means that lines formed here, you would expect convective redshifts, because that is how the velocities are changed. A further detail here is that granulation is not actually a phenomenon of the stellar surface. If as a surface we mean like optical depth unity. It is a phenomenon of that layer in the atmosphere where the energy transport changes from convective to radiative. In the case of the sun, this transition is just below the visible surface. And that's the reason why lines formed deeper down, like weak lines, are more strongly affected by convection. In hotter stars, F-type stars, there's a naked granulation. We see everything on the surface. We don't have this difference. In cooler stars, this transition is below the surface, not much, maybe just 100 kilometers or so, but it's deep enough for lines not to be visible. And so the contrast on a K-type star on the surface is very much lower, not because the convective motions are so much lower, but because they're hidden from sight. Another point to take down from 3D models is that the averages one uses sometimes don't exist. This is a plot where you see the pressure here, and here's the temperature, and this is model for Procyon, and each point here is the combination of various points in the model. So you have sometimes a certain pressure, sometimes the given temperature, and this is then the cluster of points. The average here is special because it's a very rare combination of parameters. The average is something that just happens in a freakish coincidence. It's a very rare occasion on the star. And this, of course, has implications for whatever one is computing, unless the quantity to be computed also follows a linear averaging of temperature, pressure, and so on. One measure how to measure or quantify these differences is looking at line asymmetries and spectroscopic line shifts. Here we have a cluster of lines. Each thin line is one particular time in a simulation. The bold lines are averages, and the averages are shifted. This is now a convective blue shift from what would be the, say, neutral wavelength position. So how can you measure, quantify these wave shifts? Can you use laboratory wavelengths? Of course, one has to start somewhere. But what is the accuracy you can obtain? And there is a limitation in laboratory wavelengths that limits how precisely you can determine convective and other spectral line shifts. This is a plot by comparing a histogram, comparing the wavelengths, laboratory wavelengths of about 1,000 iron lines from well-known and very respected databases, VOLD and NIST. And you will see that there is a spread roughly 50 meters a second or so. And that is typical for neutral iron lines. It gets worse for ionized lines. It gets better for resonance lines. But you say maybe you can average many lines to get a better value. Well, not really. If you look here, the average median is shifted between these data sets, and that just exemplifies the limitations in laboratory wavelengths and also the need for better laboratory data. Basically, one needs one more decimal place than we have currently. So how does one go about to determine these convective shifts? Well, you can try theory, assuming you believe it. And in such a case here, to the right are the line profiles and their bisectors from a one-dimensional model with exactly the same line list, the same parameters as far as possible as the three-dimensional model to the left. In the 3D, of course, we have the line bisectors and the line shifts, while they cannot even exist in a one-dimensional model. And if we have high enough spectral resolution, we can start seeing funny things with the bisectors. Here is for a somewhat hotter star, F-type star, the bisector C-shape, and there is a sudden blueward bend near the continuum. Where does that come from? Well, such things are signatures of the inhomogeneity of line formation across stellar surfaces. There are line components coming from granules, and there the pressure is higher, the gradients are stronger, larger, and the lines become stronger. They become stronger, and they start developing damping wings, like more Lorentzian wings. So the blue shifted components have these extended Lorentzian wings, while the red-shifted components, mainly intergranular ones, are more maybe Gaussian-like. And when you sum these things up to the continuum, then the Lorentzian wings from the granules sort of dominate, and you get such a blueward bend. So that is not a sort of computational error, it's just a further signature of inhomogeneities across the stellar surface. We can do this for example, a solar model, and differently strong lines have slightly different bisectors. One can do this for, say, a series of stars, F-type, go to solar, and all the way to maybe K-stars, where the bisectors are insignificant. As I said before, that's not because convection as such is so much weaker, but because the granulation is hidden from sight by an overlying layer. You can repeat this for iron too, and there will be subtle differences between what is neutral iron and what is ionized. You maybe noticed in the previous plot that the spectral resolution we're using is what we call hyper-high, because the worst, like ultra high already, this inflation has taken care of this. So with that we mean like 1 million or thereabouts. And you need this to resolve the shapes of lines. These are observations of some solar line at a sort of regular resolution of 100,000, that's this line, then increasing to about 200,000 and 700,000 at the top. Now, why do you need this resolution? Well, if you have 100,000 in velocity units as 3 kilometers per second, a typical photospheric line will have a width of maybe 12, 15 kilometers a second. That means with 100,000 you have 3, 4, 5 resolution elements across the line profile. The bisector is shaped by the position in opposite flanks of the line. So this gives you 2 or 3 points on the bisector. With 2 points, you can of course tell if the line is skewed one way or the other, but you cannot of course tell the shape, not to mention things like this bluebird wind we had before. This also brings us to the issues of spatially resolved spectroscopy, where the solar case has been studied. This is work by the Göttingen group, where they have positions on the sun here across the solar disk, and a series of observed line bisectors going from the disk center to the limb, and also corresponding models where the line bisector goes from blue shift near the line center towards overshooting into red shift at the limb. We can do something, we can start trying doing something similar with planets, with using exoplanets as masks, as shadow masks that are crossing the disk of the star. So in principle, if we have high enough signal to noise, high enough spectral resolution, we follow the changes in the spectrum of the sun, of the star plus planet, we subtract them in a suitable manner, and we get what is behind the planet during the time of transit. This is something for one well-known star. This is how things look like to scale. What we have here, the dashed gray is the line profile outside transit. The blue profile is reconstructed profile at closer to the center of the disk, and the brownish profile is that further to the limb. So you can see the difference. For example, at the disk center, the line is deeper. At the close to the stellar limb, the line is broader. Why? Because granulation dynamics is such that the horizontal velocities are greater than vertical ones generally, because the gases rise and they must turn over before the star ends, so to speak. So you have more broadening closer to the limb. There is, of course, a velocity shift between these two instances, because that is, of course, a stellar rotation. In this case, you can see it is prograde. So you can start doing these things, doing spatially resolved stellar spectroscopy. This also, combining this with modeling, we can start asking questions, what can we do beyond the classical Rosetta-McLaughlin effect, where of course we have the classical thing that star is rotating, we have Doppler shifted profiles, but as we saw in previous reconstruction, lines are typically deeper at the center of the stellar disk. So if a planet is covering that part of the stellar disk, the average line profile gets shallower. And the same thing for the width and the wavelength. So here we have planet position across the stellar disk. Here is the depth at the disk center. The planet covers the deepest part of the line profile, changing line profile, and the line becomes slightly shallower. The wavelength changes because we have intrinsic center limb changes of the wavelength. And you can ask, how does this work out in, say, practice for practical cases? Now here is, again, for a well-known star. We have here wavelength, what is dotted is what we would expect for a cross across the stellar equator. What is red is what we expect for the actual impact parameter for this particular system. We apply this and take the best data we find from Espresso. This is work from Nuno Santos et al. And the best transit they observed, which is then, this is then the Rosetta-McLaughlin effect, the well-known one. And down here we have the residuals. That is, for the best fit, what remains to be modeled. And this is what we predict from the center to limb change of stellar line wavelengths. Is it there? Is it not there? Well, I'm not arguing pro or false, but that is what you expect. And no matter whether you think this is a detection or not, this shows that these effects are becoming detectable with espresso-like instrumentation. And so this is a one step beyond the Rosita McLaughlin. Another thing of time-dependent modeling is, of course, that they are time variable. So instead of, say, computing the average line profile spectrum over time, averaging over space over time, we sample the spectrum at each, not each computational step, but each snapshot during a simulation. And this gives you, produce a movie of high resolution stellar spectrum atlases. And we watch these movies. Well, it sounds like a boring thing to watch such movies, but you watch these movies and you look for changes, systematic changes in line parameters. And this is one such case where this is then each profile is what results from the simulation area during one point in time, and this is the same thing zoomed up. And one can start asking questions. How do different lines change? How do they vary during the evolution, in this case, of non-magnetic granulation? And the result is that, yes, there is jittering, which if you scale to the full solar disk is about 2 meters a second. But the jittering is not identical for all spectral lines. It changes depending on the strength of the line by roughly 1/10 of its value. So if the jittering is 2 meters per second for an average line, it may be 2.2 meters a second for a different line, 1.8 meters per second for a different line. So this is one thing which in principle could permit to get rid of or understand where these small-scale, short-term jittering comes from. One can try to find the origins, and while this is not any detailed modeling, if you take the temperature versus going into the star, one finds that here, the weak lines formed roughly here at optical depth close to unity, but the stronger lines form where there is higher up and there is more spread in the parameters, and they have more latitude to roam around. We can observe spectrum microvariability because extreme precision radial velocity spectrometers also enable extreme precision stellar spectroscopy. We selected 1,000 spectra from HoRSEs North. The sun is a star, and this is the variability between 3 summer seasons, indifferently colored, for ionized iron lines and iron lines in the blue, the green, and the red. And they are changing their equivalent widths, not by much. The quantities are tiny compared, for example, to changes in the chromospheric indices. But the sun is not, of course, not stable, not on the sub-percent level. We can ask things about more complicated lines or more specific lines. This is about the magnesium lines. And this is the Grotrian energy diagram. Here is the transition for the green magnesium triplet. And here is a forbidden line, semi-forbidden line that goes from singlet S to triplet D, which is, as a forbidden line, is normally of a very low transition probability, but because its lower state is the same as the magnesium ground state, the line is still quite significant, quite strong in the actual spectrum. So it can be measured. And this is, again, for 3 summer seasons, the changes in equivalent widths between the different lines of the magnesium B triplet, B1, B2, B3, and also here of this forbidden line. The lines B1, B2, B3, they have systematic changes relative to one another. They look significant on this plot, but it's only 0.5%. But the forbidden line stays constant within measurement limits. It is probably telling us something. I'm not sure exactly what, but one side comment here is that the sun or stars are not perfectly stable in their spectral lines. And this puts also certain limits on how, irrespective of computational sophistication, how precisely one can model, for example, stellar spectral lines. If you make a detailed model that fits for example, these magnesium lines, that may fit them in July 2024, but it will no longer fit the star in August 2024. So there is some sort of a limit. I'm not sure what that implies, but there is. It's not just chromospheric lines that change, but also, of course, photospheres. I make some comments now about the gravitational redshifts which appear in the literature and sometimes in a somewhat confused manner. The Sun has a gravitational redshift, and it can be computed from definitions. The IU definition of the normal solar radius, that's the definition. There is a definition of the gravitational constant times the solar mass, and the speed of light, of course, is defined from the SI unit of time and space. If you combine these, you get the solar gravitational redshift from the solar surface to infinity. And it is a definition. It's not a theoretical fit. It's not an observational quantity. It is so by definition. But the gravitational redshift changes with distance from the solar disk center. So if at the center of the surface it is 636.31 meters per second, it is already smaller if you go up in the chromosphere, and if you're already in the upper chromosphere, you're already many tens of meters away, not to mention the corona. This also means that if the Sun is oscillating for whatever reason, with the solar cycle or because of evolution, you will change the gravitational redshift. And here is some work that shows how much, in the case of a Sun, 100 kilometers, the Sun's radius has to change in order for the gravitational redshift to equal the signature of an Earth-like planet around it. So if one is looking for a 1 year period, you better understand if the Sun is not oscillating on that period. But going back to the quantity of solar gravitational redshift, now that quantity is to infinity. At 1 astronomical unit, we're still only 200 solar radii from the Sun, and we still have a solar gravitational redshift of roughly 3 meters a second. If we observe this thing on the Earth, there is a special relativity effect that enters. Namely, we're moving, and there is a transverse radial velocity that comes from special relativity of a few meters per second. And with orbital speed, we get 1.5 meters extra redshift. And this all sums up to roughly 635 meters per second relative to the solar photosphere. So if you want to have it more precisely, you have to start specifying where on the Earth you are or in what point in the Earth's elliptic orbit. Final comment on this is that it is sometimes said in literature that gravitational redshift will be some sort of a test of general relativity. It is not. It follows from the energy principle. Light must lose energy if it climbs out from a potential well. And this applies to any reasonable theory of gravity, general relativity, modified Newtonian dynamics, scalar tensor, or whatever. My final points here will concern high-resolution spectrometers. If you come to Potsdam, you can walk along the Spektrumweg, and you can agree to meet someone at the maybe sodium D lines or somewhere. This is a plot of the solar spectrum taken with PEPSI instrument or the Large Molecular Telescope with spectral resolving power almost 300,000. We'll have a great spectrometer in the years ahead, NDs on the ELT, and no doubt that will be an excellent instrument and enable extremely many interesting studies. However, its telescope is extremely large, but its resolution is not. So 100,000, that is, of course, excellent, but it is only HoRSEs. It does not reach the 200,000 of espresso, does not reach the 300,000 of PEPSI, does not reach the 400,000 of the Clef spectrometer, about which there's a nice poster out there, for the Magellan telescopes. Now, of course, it is difficult to design such an ultra-high resolution instrument for very large telescopes because the image scale gets gigantic. With the ELT, the focal length is approaching the order of a kilometer. And obviously, it's non-trivial. One possible solution is to use adaptive optics. That is what the Clef design is using. Maybe other solutions. Because in this case, it's possible to make the spectrometer reasonably small. But I would say, conclude here, is a grand challenge is how to design and ultimately build an ELT spectrometer for and hyper high resolution. That would enable studies of spectral line shapes, not only their positions or on their existence, not only for stars, it will also enable studies, for example, for the asymmetric lines in quasars and whatnot. So with that, thank you for listening.
Hello?
Okay, let's welcome the next speaker, Vatsal Panwar. Related to the question about spottedness by somebody in here in the audience, we will now hear about stellar activity and impact on modeling exoplanet spectroscopy. Go ahead.
Thank you. I should thank Dainis Dravins for an excellent introduction on so many complications and so many sort of specific things about stellar atmospheres modeling, which is quite relevant to what I'm going to be talking about. So this is an ongoing work I've been doing with Heather Segla, Matteo Broci, Ginger Frame, and Marina Lafarga Magro at University of Warwick. And the idea here is to really try to evaluate in sort of quite simple situations how stellar activity would affect the cross-correlation measurements that we are so used to hearing about for exoplanet atmospheres. Okay, so we're quite familiar that stellar activity is a bit of an issue for exoplanet detection. So this is a time series of radial velocities of the sun taken from HoRSEs north across 8 years. So the radial velocities are on the top panel, and what you see in the panels sort of parallel to it is how all the different activity indicators, so for example, at the bottom is the calcium HNK lines, also change. So there's quite a sort of clear impact of stellar activity on the radial velocity of a star that we observe. And this is also an issue for exoplanet atmospheres. So going back to low resolution for like just one slide, we get this effect because essentially what you're seeing is the source of the light that you're getting when you're trying to measure the properties of atmospheres is not the same as we assume to be a quiescent disk. And this has been seen for many JWST observations, including this one for TRAPPIST-1b, where you see this sort of slope towards the bluer wavelengths that's coming from the stellar spots or like dark spots or bright plage that are unocculted on the stellar disk. Oh yes, sorry. Going back to high resolution, this is I just made a bit of a list of some order of magnitude things to take into consideration about flux and velocity. If you think about just the flux in terms of the different things that are changing when we are doing these observations, the contribution from the planetary lines is up to about 0.01 to 0.1%. And from just center to limb variation, that can go up to almost 20 to 30%. And from spots and plages, so this has been seen from rotational modulation in photometry, from Kepler, from TESS, and that can be up to about 2%. Talking about just velocities, just thinking of like the Doppler shift from the planetary atmosphere by the planet itself, for a typical hot Jupiter, that's of the order of about 50 to 100 kilometers per second. Whereas if you just consider rotational broadening, so there is a really cool paper looking for reflected light from 51 PEG-B by Eleanor Spring, where you can see that like the typical sort of rotational broadening that you expect is of the order of 5 to 10 kilometers per second. And there's also stellar rotational broadening on top of that. One thing that is sort of was asked by, I think, Vivian, is about stellar sort of spot contribution. So I have a slide next after this where for the sun, it has been measured, the convective blue shift to be of the order of around 300 meters per second. And kind of sort of overlapping between the flux and the velocities is the Rossiter-McLaughlin effect, and that can be of the order of about 1% in flux or about 10 meters per second in velocity. So this is just on the left, the sort of, because spatially from the sun, you can actually resolve the spectra coming from, like the cross-correlation function coming from the spot itself. And if you see the red line is the one that you get from the spot itself, so that's kind of the asymmetry, you see that. And it's also kind of red shift. It's not as blue shifted as it should be. just considering convective blue shift. And that's about of the order of 300 meters per second. And this has also been seen for plages, which are sort of bright spots, essentially, of up to about similar order. And the source of like this stellar activity at high resolution is not something new. It has been seen in many different forms. So here's an example of the Doppler shadow that's seen quite often for WASP-189. In this case, where you see this sort of dark sort of diagonal line that is almost overlapping with the planetary signal towards the egress. So that is something you have to take into account if you're too close to that. So if you say, for example, the planet is in a polar orbit, that will actually be much closer to your planetary signal. Another case, which is also quite famous, is for HT219. So these are the data from Espresso. And on the top, what you see is what you get from the data itself. And the second panel is kind of the modeling of the Rosetta-McLaughlin and center-to-limb variations from the sodium lines. And on the third panel, this is kind of looking at just individual lines. So for helium, for hydrogen, for H-alpha, and for sodium. You can actually see this sort of correlation with the stellar activity indices. So this kind of clearly tells you that there's definitely a very significant thing to keep in mind. This, particularly in the context of cross correlations, so this has already been attempted. This is an example of using a 3D stellar atmosphere instead of just using 1D atmospheres to correct for the stellar spectrum when you're doing cross correlation. And then the top is actually what you see, this sort of 3D simulation from a code called Optim 3D. And the spectra that is generated by that code has been used to correct the stellar residuals for HE189 in that case. So it kind of improves the detection by quite a significant amount. So my question is, what I'm trying to work on is, what is the effect of the temporal and spatial variations of the stellar disk on the cross-correlation spectroscopy? And the way I'm doing this is by sort of just taking a forward modeling approach and sort of really trying to understand the effect of the temporal variation in the stellar photosphere itself changing. And this is work I'm doing in collaboration with Ginger Frame, who also has a poster on some of the work she's been doing on sort of accounting for these effects in radial velocities specifically. But what I'm trying to do more specifically, so on the left, what you see are like these 3D grids that I generate for both flux and velocity, is to sort of take the spherical tile grid line, manipulate it with the, how the viewer is situated, and each tile can be assigned a spectra. And you can account for limb darkening, convective blue shift suppression, and also like the effect of each tile, sort of the way it's projected towards you. I'm also taking like sort of an initial reference for spot properties that have been measured from photometry. So there's quite famous examples of HATP11 and WASP-19. And just to sort of, as a starting point, I'm right now restricted to just using 1D stellar models. But the tiles are actually rectangular, so you can actually, in future, really put a 3D stellar atmosphere model there. And just for now, considering as if like a single spot represents the whole spot filling fraction, again, which is quite a big generalization. Just thinking about transmission for now, and just thinking of planet as an opaque disk, so not really considering the extent of the atmosphere occulting these different tiles. And just looking at K-band, because that's where we are quite interested in measuring all these molecules, like carbon monoxide and water. And also assuming that the PC is done correctly. So this is sort of the axis of this modeling experiment. So I'm going in sort of changing the spot contrast. So these low and high values are actually also sort of measured from spot occultations from transit photometry. And for the velocity, so yeah, this is an example of a WASP-19, for example, from ground-based photometry, actually spectrophotometry, that the spot contrasts have been measured. And this is just a sort of plot I picked up from NASA Experiment Archive that shows you the spread of measured rotational velocity. There's no error bars there, but kind of tells you like what's the extent it can go. So I'm kind of still going up to like 50 kilometers per second just to not go too crazy. So these are sort of just the lengths of different simulations. I'll try to play these. So, oops, sorry. Kind of shows you that On the left, it's a slowly rotating star, and on the right, it's a faster rotating star. So that's kind of the difference you get when a star is rotating 5 times faster. So you can see that the spot is sort of crossing these different sort of red and blue shifted parts of the stellar disk. And the idea here is like, how does that actually become apparent in your cross correlation or even log likelihood signal that you're trying to measure? Okay, so here is sort of the main preliminary result plot. So what I've done is I've injected a planet at, actually the line is wrongly marked, it's on plus 15 kilometers per second. But this is in cross correlation space. But you can already see that for the case of sort of slow rotating, low contrast spots, the signal in red, which is sort of from the injected model, is quite close to the dashed lines, which are from like a quiescent star with no spots. But if you take into account this high contrast spots and faster rotation, so that is around 50 kilometers per second, you see this, I don't think you have to squint too hard, but you can see this sort of artifact popping around 0 kilometers per second. And this is in just like sort of cross correlation signal to noise space. But if you convert this into log likelihood, which actually takes into account the variation, or like the variance in the model itself, then you can actually start to quantify it in terms of statistics. So I'm just going to zoom into that. And it's, I mean, I injected a huge model, and even then, the difference you get is just about up to log likelihood of 200, which is, I mean, so again, this is like using just a simple Phoenix model and just sort of two sort of extreme cases. So yeah, so, it's still an ongoing work, but the take-home message now is that it's quite likely that these high-resolution cross-correlation measurements that we are doing are susceptible to stellar activity. For transmission, this can be, at least from these extreme cases, the effect could be quite significant statistically. The next steps I'm thinking of doing now is to sort of try more realistic models, so going for sort of something more realistically spatial distribution of these activity features. So like for sun, for example, we know how these stellar spots are distributed usually in which latitudes. Also accounting for the effect of BCA, does BCA get rid of these sort of artifacts and we don't have to worry about it? Another question. Also like emulating this case for emission and yeah, using like a more sophisticated 3D stellar atmosphere models. And yeah, any suggestions, questions, please let me know. Thank you.
Sorry, just a really quick announcement for the speakers. If you guys could stay close to like the podium so that you stay in the stream, that would be great. Thank you.
Sophia, I'll give you it.
Does this actually work? That one works, okay. So I realize my talk title might have been mildly misleading because I'm actually talking about the reflection spectra of exoplanets and not stars. So, sorry about that. You've probably heard quite a lot about the emission spectra of planets and the transmission, but less about the reflection. And this is kind of a shame because reflection spectra offer quite a lot of unique and complementary information to transmission and emission spectra. Specifically, they can help you constrain the clouds and energy budgets of planets, which is key to understanding their environment. At high spectral resolution, we have no confirmed detections of an exoplanet in reflected light yet. And this is not for lack of trying. We have tried many times. The Martins et al. 2015 paper did have a detection in it, but subsequent analysis of the data set and with additional data didn't reveal a detection. So the top right plot here is the non-detection that was retrieved by spring 2022. And the one underneath it is an injection with the parameters that Martins 2015 detected. And you would have been able to detect if it had actually been there. So unfortunately, it seems that that one wasn't real in the end. I also would like to shout out Jane Birkby's poster on how we are now starting to push down the contrast limits on some of these detections to 10 to the -6. So what this means actually is that a lot of the planets we've targeted have had quite low albedos. They haven't reflected much light, so we haven't been able to detect it. This is not true of all planets, though. We do know of a few from secondary eclipse measurements that are reflective. One of these, LTT 9779b, is incredibly reflective. It's got an albedo similar to Venus. It's also kind of weird, because it's a resident of the Neptune desert. And its orbit's been measured 3 times by 3 different authors, so we know it's definitely in here. We've looked with JWST at transits and got a kind of reasonably flat spectrum. So what this means is that the atmosphere of this planet is either very high metallicity, or it has a very high cloud deck, or some combination of the both. But unfortunately, transit observations can't tell. But with high resolution in reflection, as we heard earlier, you'll be able to see the spectral lines peeking out from the clouds if they are there. So hopefully, at high resolution, we'd be able to learn more about this planet. And so I have espresso observations of the secondary eclipse of this planet, so we can hopefully detect the reflected light. This analysis is still in progress, so I don't have a final result for you yet. But I want to highlight something quite important I've discovered with an injection. So this is not a real detection, this is an injection, and quite a strong one at that. Hence the reason it's a negative KP, not real. So what I've done is I've injected a planet with one of the ephemerides, and then recovered it with an ephemeris that's 20 seconds wrong. And if I recover it with the right one, you can see that the signal shifted slightly. So before, we had a 4 kilometers a second blue shift in our detection, although we have no dynamics in this model at all. And then when we use the right ephemeris, it goes back to normal. This is kind of a problem because quite a lot of planets don't have very good ephemerides. This plot shows the planets with orbital periods less than 3 days in NASA Exoplanet Archive, what the error in their orbital period propagates to today in seconds. The dashed line shows 20 seconds, and the solid line shows the equivalent in fraction of the orbital period. The numbers that NASA Exoplanet Archive gives for LTT 979b are actually from the Jenkins 2020 paper. This is an older ephemeris, which is up there and quite bad. The newer ephemerides do better. But what I'd like to also point out is that we can use our high-resolution data to model the orbit of the planet, basically by doing RVs with the stellar spectrum. So these are my 4 nights of data, and these are the stellar RVs, just taken from Espresso. This upward trend is not a systematic. This is the reflex motion of the star being caused by the planet. And so we can fit the orbit, but we don't do very good. This is because we've only got the secondary eclipse, and so we can't really constrain the orbital period with this. But there is more data for this planet than just Espresso. We have the original HARPS RVs used to confirm the planetary nature of this object. We have the test light curve that was initially used to discover it. We've got the secondary eclipse Espresso observations, and there was also another program to look at the transits with Espresso, so we have those. And we can fit all of this data, and now we can constrain the orbit pretty well. In fact, the error is now roughly 20 seconds. The nice thing about this is if you ignore the light curves, so for example, pretending the planet for a minute is non-transiting, you can do much better. So the gray here is just fitting with the HARPS only data. These data points are quite sparse, so they're not very good for fitting the orbital period. But if we add in the Espresso observations, we are now much better at constraining the orbital period for a pretend non-transiting planet. We also put much stronger constraints on the eccentricity and the semi-amplitude, which is important for determining the mass of the planet. Now, I'm going to keep working on this, and so watch this space soon with potentially detecting something. And I have a vested interest in getting this to work because I want to find aliens. And this is because for Earth-like planets, at wavelengths shorter than 3 microns, the spectrum is going to be dominated by reflection, which means if you want to look for biosignatures such as oxygen, you're probably going to be looking in the reflection spectrum. And this is coming soon. So with the ELTs, we're going to start to be able to characterize some of the first potentially Earth-like planets. And so what I'm going to talk to you about now is whether we can detect and characterize Proxima b, which is a non-transiting planet, with harmony at ELT. So this would be using a technique called molecule mapping. Basically, we take an image of the star, and then take a spectrum of each pixel in that image. This is what harmony will have here on the right. It also does something quite fancy because it digs a dark hole around the star, so there's less diffracted starlight in that region, and hopefully we'll be able to see the planet. It also covers up the star with a focal plane mask so that we don't saturate the detector. On the left is an example of the spectral region that we'd be looking at, and will be sensitive to things like CO2, H2O, and CH4. Unfortunately, we won't get a spectrum quite as pretty as this because we will have noise. So this comes so I'm going to rotate now into the spectral axis to show you how this works. So this is not a time series. The y-axis is space. We still have the vertical lines from the tellurics and from the star, but the horizontal variation is due to the PSF. And we can use all of this data to create a model of the stellar spectrum and the tellurics and remove them, and what we end up with is noise. The little EP tag is where the planet should be. You can't see its spectrum directly. But what you can do is you can cross-correlate with a model of the planet spectrum. And then you get a localized increase in the cross-correlation coefficients at the right velocity and the right location in space. We can then flip, because this is a 3D cube, we can then flip into the space axis, and we can see that the detection is also localized in space, which means we've detected the planet. Now, that focal plane mask I mentioned earlier, this is where Proxima b should be. It's behind it. So I've been looking into how we can sort of fudge the situation to try and detect the planet. So if we observe without a mask, or if we offset the current mask, we can get detections. The problem is that we are not allowed to observe without a mask because it will saturate the detector, and I've been told no. And the offset mask, unfortunately, requires us to know the orbit of the planet, which is not a given before the ELT will come online. So I've also looked at whether if we change the mask, whether we could get a detection. And the answer is yes. Different masks perform slightly differently, but in general, we'll be able to get a detection of the planet within 20 to 40 hours of integration time. The shaded regions here are actually the 1 sigma errors on the signal to noise you'd recover, and this is mostly due to just photon noise and different draws of the noise. Excitingly, the Harmony team is actually now looking into changing the mask, or potentially the appetizer, which will shrink the inner working angle slightly. Finally, I also looked at when you cross-correlate with different models, what the detection strength is. So obviously, using all of the spectral lines you have, the planet spectral lines and the star spectral lines gives you the best signal. Most of this seems to be coming from the planet absorption lines, and specifically the CH4 lines. For the CO2 lines and for the stellar lines, we don't get a detection. And that is because the residual stellar spectrum and the residual tellurics in our data is creating lots of correlations and is unfortunately hiding these signals. And so in this case, we can't use these lines to get a detection. Okay, so I'm just going to summarize really quickly, and then I have one more thing to show you. So in summary, ephemerides matter. High-resolution cross-correlation spectroscopy is quite tricky, and particularly removing the spectral lines of M dwarfs well enough in order to get a detection. But we are slowly learning how to do this, and so fingers crossed for the future. With the ELTs, we're going to start to be able to look at the first, potentially Earth-like exoplanets. And with Harmony at ELT, we'll be able to characterize Proxima b within roughly 20 to 40 hours of integration time. My final little thing is a shout out to my 2023 paper of how we can use reflection at low resolution to, in polarized light specifically, to detect liquid water on exoplanets. And this is using rainbows. Okay, that's it. Thank you.
Keep us in place.
Okay, can everyone hear me? Okay, awesome. All right, yeah, I'm really excited to be here today to tell you all about some work I've been doing on using data-driven tools to infer detailed elemental abundances for M-dwarfs, and then applying those tools to large M-dwarf samples in the Sloan Digital Sky Survey. So in general, it's really important for us to develop robust methods of characterizing M-dwarfs because they are the most common type of star. So they make up about 70% of the solar neighborhood. But because M-dwarfs are so cool, it's possible for molecules to form in their atmospheres, and that makes it very difficult to model their spectra and to extract out information on their chemical compositions. And that's because molecules introduce these like dense forests of lines in the optical and near-infrared regions of spectra. So in this plot here, I'm showing 3 examples of synthetic spectra generated with the code spectroscopy made easy. They're organized in this plot from top to bottom as hotter to cooler. And you can see that the bottom spectrum, which corresponds to like a fake cool M-dwarf, is the most complex because of the presence of these like complex molecular lines. And in general, we don't have a really good handle on these molecular lines in terms of their information like locations, opacities, et cetera. And so for these reasons, spectral synthesis codes that make use of line lists, they're pretty good at modeling stars that are warmer, like in the solar-like regime, but they really struggle in the cool star regime where M-dwarfs are. So some studies have gotten around this by constructing their own boutique line lists that include more M-dwarf spectral features. Oftentimes to get these, or to get the information on these features, these studies made use of like empirical relations between different abundances or like how these abundances change as a function of temperature. But in general, this type of analysis is very time consuming. It can take a lot of time to like run these codes. And for this reason, a lot of these studies have only been able to characterize small samples of M-dwarfs, like maybe 20 stars at a time or so. So alternatively, we can choose to bypass spectral synthesis codes and physical models altogether. So in this project, we're making use of the Canon, which is a data-driven framework that allows you to basically infer stellar parameters and abundances just given stellar spectra. So it doesn't make use of physical models at all. It's named in honor of astronomer Annie Jump Cannon, who established the first and still current stellar classification system. So yeah, like I said, the Canon doesn't make use of any stellar physical models. It only needs spectra, and with spectra, we're able to infer stellar labels, where labels here is just like a machine learning terminology way of describing like physical parameters like temperature and log G and chemical abundances. And the Canon can like infer any sort of abundance or parameter label that you want it to, as long as you have that information in your training set. So more on that. So the Canon works via a 2-step process. So in the first step, or the training step, we basically make use of a training set of stars and their spectra, where the stars have well-measured abundance and parameter labels. And then we use that training set to train a set of flux models where there is one single flux model at every pixel in the wavelength range of our spectra. And then in the second step, or the test step, we apply that set of flux models to the spectra of stars so that we can infer their parameter and abundance labels. So because we're actually using like a set of flux models, the Canon is actually generating a synthetic spectrum for each star. So I'm showing an example of that here in this plot with a random like real stars spectrum in white and the Canon flux model overplotted in red. So we can do this like for every star in our test set, and in that way we can infer their parameter and abundance labels. Okay, so our goal in this project was to basically use the Canon to construct a model that allows us to measure detailed elemental abundances for large M-dwarf samples in the Sloan Digital Sky Survey, and we want to get abundances beyond iron. So to do this, we wanted to construct basically a training set from SDSS 4 and 5 data releases. And I should mention that SDSS has its own built-in stellar abundances and chemical parameters pipeline called ASPCAP. And ASPCAP makes use of spectral synthesis codes and models, and so for that reason, it is like not very reliable for cool stars like M-dwarfs. So how did we use SDSS to construct this training set of M-dwarfs for the Canon? So what we did is we actually looked for binaries in SDSS, where one of the stars is a solar-like dwarf, and the other is an M-dwarf. And then because the ASPCAP pipeline uses spectral synthesis codes. It is accurate for solar-like stars, so we can assume that the ASP-cap abundances for the FGK dwarfs are good. And then we can tag those to the M dwarf companion, because we can assume that binary companions formed from the same molecular birth cloud, and thus were born chemically homogeneous. And so now those M dwarfs that have been tagged with the FGK abundances of their companion form the basis for our training set for the canon. And I should mention that we found these FGK M binaries in SDSS by just cross-matching SDSS with a catalog of binaries from Gaia DR3. And when we did that, we found about 50 FGK M binaries in SDSS4, an additional 50 in SDSS5. So I'm illustrating those binary pairs here with their GMAG plotted against their T effective. The bound pairs are connected via dashed lines, and both of the stars are colored by the iron abundance of the FGK companion. Okay, so then we wanted to basically assess the accuracy of the stellar abundances of our training set. So to do that, we ran a leave one out cross-validation scheme on all of the M dwarfs in our sample. I'm not going to explain what that is here for the sake of time, but if you're curious, I can explain more later. So these panels here illustrate our results from the leave one out cross-validation, where each of them represents a single elemental abundance. And what I'm actually plotting here is our inferred elemental abundance from the canon on the y-axis versus the FGK abundances on the x-axis. And the points are colored by the chi-square difference of the model spectral fit to the real data. So what we want to see here is adherence to a one-to-one line, because that would indicate that the FGK abundances well represent the M dwarf spectra. So that kind of gives you a sense of like, okay, the chemical information actually is accurate in this training set. And you can see that for the most part, that seems to be true. And I'm also plotting, or I'm also showing the RMS scatter in the upper left corners of these panels between our inferred abundances versus the FGK abundances. And you can see that the scatter in general is pretty low. It ranges from like 0.1 to 0.17 dex across all elements, which is pretty decent. And it's also really good because we're getting a wide set of elements here. So we've got like a lot of volatiles that are common in M dwarf molecular species like carbon and oxygen. We also have a lot of refractories, particularly those that are well represented in planet-forming material like magnesium, silicon, etc. So this is really showing for the first time that we can use data-driven tools like the canon to infer detailed abundances for M dwarfs. And another test that we did to just assess the reliability of the training set is that we checked to see if they can reproduce expected metallicity tracks in the HR diagram from stellar evolution. And when we deployed this training set on a random sample of M dwarfs in SDSS, we found that to be true. So our data is shown in the plot on the left, and you can see those metallicity tracks in the colors there, and you can compare that to like what we expect from stellar evolution as like exhibited by the plot on the right, which is from a different paper, and you can see that they match pretty well. And we're doing much, much better than like the ASP-cap abundances for M dwarfs themselves. So if we try to like reproduce these metallicity tracks with the M dwarf ASP-cap iron abundances, like in the plot on the right here, you can see that the metallicity tracks kind of disappear. So we're doing a lot better than like the abundances that are coming out of the SDSS pipeline. And I thought we might also just want to see what a spectral fit looks like in detail. So this is another example of like a random M dwarf with the spectra in white and the Canon flux model fit to it in red. And I'm highlighting some OH features here that we use to calculate the oxygen abundance. So this is kind of just what it looks like on the inside. Okay. So to quickly summarize, so we've used the canon to basically construct a model that allows us to infer M dwarf abundances for a wide set of elements. And we did this by constructing a training set of M dwarfs using the SDSS 4 and 5 data releases, where the training set are drawn from FGK M binaries. And in this way, we can like infer a wide set of elements here. So now the only thing left to do is to deploy this training set on all of the M dwarfs in SDSS 4 and 5. The last time I checked, this is like over 100,000 M dwarfs, so be on the lookout for this value-added catalog in the next couple months, and I'm really excited to see what the community does with it. I'm really excited to investigate planet formation pathways with this, and there are, I think, like tens of thousands of TESS M dwarf planet candidate hosts in SDSS, so I think we're going to have an excellent sample to do this. So yeah, that's all I have. Thank you, and I'm happy to take questions.
And the next speaker is Andrea Chiavassa from Nice, and he will talk about 3D radiation hydrodynamics models for specific group of stars or type of stars, namely M dwarfs.
Hello. Hello, everybody. Thank you, Maria. Use name and fear to destroy. I don't believe in the 3D LTE model anymore, but I present this anyway. So this is on purpose. You don't see it because now you see better. So I depolluted the signal, so the planet now can see what is behind. But the signal of the star, for me, is still the important part. So I will present this first work we are doing. And I start with showing the people are involved. Apart myself, there are two people, Lionel and Thomas Masseron, working on star. And Matteo is also here. The idea is just to show that the collaboration between planet and stellar groups works very well. And so this is one of the things I want to point out. This is work in progress, so take it like still to be finished. So first thing I want, has already been said, something, so I thanks also Dainis for this morning. I will go fast for something, but I still want to show you again that the stars are not black bodies. This is a synthetic spectrum of the sun. Is already visible, there are lines and molecules, but it's even more visible when you are looking to other objects like N dwarf, so it doesn't work, or even brown dwarf. So you see really the signature of any kinds of atoms on the short wavelengths and molecular transition on the going to the infrared. We do then, we saw already this granulation effect, so it's some small videos, convective, rising material. The size here I put Italy because it's my country, you can put it everywhere, but it is about 1,000 kilometers for the sun, so it's about 5 minutes. So the sun changes its aspect every 5 minutes. So we said a lot about that, but maybe we didn't see this in this way. So I try to show now with this kind of simulation how the spectrum changes in particularly important regions, which is the CO regions in K-band. So you see the time going up on the right-hand side, time going up, and you see the spectrum with these two reference lines going up, and even they're getting lower, and over the shape of the lines is changing. This, you can imagine, during the planet transit, is impacting your signal. This is from the temporal point of view. Now let's see from the spatial point of view. Just look at the small circle on the bottom left, and now it's going up, and the line is forming on the right-hand side. So you see the line, it depends on what are probing. So rising material or intergranular lines, so something that Maria Philip just showed as well, is changing a lot. And so at the end, if you just pick up two particular lines, one from the red or the blue star, you see that either blue shifted, either red shifted, and the average is the middle. And so it's not, so this is one of the reasons that also Dainis was talking this morning about the convective shift, but it's also the reason why the abundance are also impacted by this, and they are variable as a function of time. Last point I want to mention, these lines in the stars are also in the planets. Let's have an example, K-type star, so the yellow one, compared to a magnetized, so enlarged spectrum of Jupiter. The CO is there in both cases. So when we go, they actually are fitting in the same position. So this is another reason why we really need to master the star and the position of the line, of the position of the lines in the star to better have a point on the detection and characterization of the CO in the planet. Okay, I will not repeat everything that's been said like here, but just want to say a word about what Maria was mentioning. So we do actually Cartesian boxes with the equidistant pixel, let's say this, grid points that you see there, and then we actually move the box and we compute the spectrum from each point rotating, let's say, the box, and we cover the first surface. In everything I show you here, we did not include, everything is LTE, sorry Maria, and no magnetic fields for now is included, even though we are doing models in this sense, which is something, of course, very crucial for N-dwarf, but still we have some result. This model, we take them, we do spectra, as Maria and Philip just showed. This spectra, so just to give you, so we have grid points, grid models of this, covering like log G as a function of TF. You have different box size. These box sides are used to patch, if you want, the full surface. And you see that the size of the boxes changes with respect to the size of the star you're looking at. And this depends on the stellar parameter. Lower log G, larger granules, hotter star, which makes also that the convection is different. So granulation size, convection turnover depends on this. For the sun, 5 minutes. For N-dwarf, maybe it's hours or something like this. So you see that in the case of the Sun and the K-dwarf, we don't see anymore the granules, but they are there and they change as a function of time. What happens now when we go to N-dwarf, so to the regime here on the bottom right? So always we have this kind of boxes for this TF of 3500, log G for pi 4.5, the model represented today, and solar metallicity. Now the boxes is even very small. So basically the boxes we use is such big in the full surface, if you assume 0.4 solar radii. And from that, we then we try to analyze and have an idea of how it works, the dynamics of the star. Let's give you some examples for this model. I pick up something like, let's say, still flying, but a bit old, so Gaia. So sorry about that, but I'm part of this consortium. I think it's important to bring something also on the market. So this is the RVS spectrum. It's about very low resolution, 12,000. So you have, in this case, selected iron lines in black and calcium 2 lines in red. So one is deeper, the calcium line, and the iron are smaller, different sizes. Then I defined the bisector that shown this morning. The bisector is the difference, so it's the distance between one side and the other side of the star, of the line, the spectral line. If there is no movement, if the velocity is constant, if it is hydrostatic 1D model, this is a straight line corresponding to the laboratory measurements. If it is not the case, like it happens in the Sun, has been shown in this model by Dainis, and we show these are a calculation on the right from the models, then there are velocities that are actually affecting that. And the nice thing to see is that this affection is not depending on, so it depends on where the lines are forming. Basically, weak lines are generally blue shifted, strong lines are red shifted. One of the reasons is just because the formation is more deep in the atmosphere, so more turbulence there, but something Dainis already said before, but I think it's important to repeat. And then this actually, of course, affect, for instance, the mask used for radial velocity, etc. What happens for the N-dwarf? So the Sun is like that. I put the reference in blue just for fun. In the case of K-dwarf, we have something like that. And we also have some particular things in the M-dwarf, which is with spanning velocity of a few hundred meters per second for these weak lines going left and right. So you see this aspect, and from that we can correlate this 3D spectrum with the 1D hydrostatic and see for these particular iron lines what is the radial velocity, the convective shift in this RVS Gaia region. So these are again all the grid models we have. All the points here correspond to a model. The color are different metallicity, just to have an idea, and the size of the ball depends if it's stronger or less strong. The shift. This has been published in 2018. There are the spectra available if you want. Now, if we add, so everything is shifting between 0.2 and 0.3 kilometers per second, so something non-negligible at all for all the stars. But in the case of the N-dwarf, when we apply even macro turbulence, which is needed in the case of 1D, we go up to 0.6 kilometers per second, so it's pretty high. Okay, let's go to the second part towards the end, which is a bit more long. So I show you now the molecular contribution of all the aspects inside this M-dwarf. Again, you see the parameter on the top. In this case, it's just a, let's say, low resolution 10,000. So you see, we pick up this region because it's Spirou, Jano, Igrin's CRIRES Plus, so it's interesting for you guys. And now if you put the full spectrum in this sense and normalize this to the continuum, I compute the continuum properly. So for me, continuum means bound-free and free elements in the continuum, so forming deeper. So I can compute this in my right transfer code and normalize by that. You see this array is not flat, and we're going to discover this why, even if you can imagine. And I divide on the left low contributors, intermediate contributors, and large contributors to the spectral line. So let's start. So we have CN, like low, chromium hydrogen, TiO, FAH, HCl, and then we go HF, and then to the large contributors, so CO, OH, and finally H2O. So H2O basically is the one that in the M-dwarf we could expect is changed even the position of the continuum more than the others. So the other are just adding one to the other. So and the black line that you see still there are atomic lines. So there are the references where this lists come from. And talking with Matteo, at that point, we started to think, yeah, right. So with this enhanced, we can maybe have a look to the line list used for exoplanet transit or exoplanet analysis and see which one could be useful to which one is better to respect to the other. Let's start to say from the easy part, which works better is the CO. To do this, we start with the simulation with this one, and we compare to dwarf observed with JANO with a resolution of 50,000. Now, what I show you, the synthetic spectra are 300,000, so much higher resolution. Still no 1 million, but 300,000. And then we made the comparison here. So you have a telluric region on the right, so just forget about that. You have a tellurical there as well. But the other two regions here, they actually correspond to two parts in which we have a quite good overlap between the red curve, which is a 3D spectra, and the black one, except the one line, I don't have the pointer. Still, we can actually, I think we can actually pretty much conclude that the CO lines list is fine. And yep, I missed that. The CO lines is pretty good, and we have good match. So that's pretty much good, and we can go to the next step. What is worse is the situation in H2. So H2 is the water, as you can imagine, is polluting a lot the signal also for what you look in the planets. So you have an example here. The black line is the observation, and the different color, different list. So ITRAN, Marvel, and Pokazatel. So the idea we had is to make a cross-correlation between data computed and observation, including on not telluric. So what does it mean? So this is a cross-correlation results. So is the Pearson cross-correlation coefficient, so it's normalized. So you have different color. Just the blue and the orange are two different regions, 2.1, 2.105 micron. And the green one is the same as the orange one, but without the tellurics. So what Matteo did here, I think he put like the data, so the synthetic data without or with the telluric and makes the cross correlation. And there is a clear offset on the wings enlargement that we can discuss later. It's due to the tellurics correlation themselves. So just take this for now. At the end, so this is my almost the end talk. So now we see just the results we have. So starting with the Pokazatel list. So you have a value of the different top with the coefficient. So it's 0.5, 0.7, 73, etc. But there is a slightly offset with respect to the 0. We can clearly see, I think, with the line I put. This shift actually increased when you use HITRAN in this case. And this, in addition to this, also this cross correlation get larger. So it means that ITRAN works less well here when comparing just to the stellar lines. And the situation is much better. So I think we have the winner here is Marvel. It's actually very centered to the center, and the start and the cross correlation profile is much narrower. So let me conclude on this, and this is where I put the HoRSEs. We have a few conclusions. So we have simulation of 3D and dwarf, LTE, but still, these are the first in spectral resolution, for which we have a radial velocity correction of few hundred kilometers per second. So something to be taken into account, this convection-related thing. This 3D second point and dwarf have returned a very good agreement with CO. That's a good point that can be used already for injection of planets and some transited analysis. Third things, we can use just the star to provide a good agreement to see which line list for the water, even for other, is the best. So in this case, it's Marvel the winner. And finally, we are ready for going for abundances. Even if they are the LTE, this would be like a good step forward, I think. What we are doing now, and I finish on these three things, we are making like stellar parameter 3D versus 1D from the stellar point of view to a better parameter, better agreement on micro and macro turbulence, abundance correction, 3D, 1D, we are doing this. Next step, like injection of the planet to see what happens. And finally, we're asking, so we're hoping if people want to also give their data and see what happens with other instruments, that would be great. Actually, we are very open to that. Just please contact me if you have the willingness to do that. Oh, I'm finished. Thank you.
The next speaker is Gloria Canocchi from Stockholm. And she will be talking about non-LTE effects.
Good afternoon, everyone. I am Gloria Canocchi, and I'm a PhD student at Stockholm University, supervised by Dr. Karin Lind. And today I will present my current work, which is about challenging sodium detections in the atmospheres of giant exoplanets using 3D non-LTE stellar spectra. Thank you, Maria, for the introduction to the 3D non-LTE. So, as you all know, transmission spectroscopy has become one of the most powerful tools for the atmospheric characterization of transiting exoplanets. And indeed, during the transit, if we focus on the upper layers of the planet atmospheres, what we see is that some of the light will pass undisturbed, some will be blocked by the planet itself, and finally some will be filtered through the upper layers of the planet atmospheres, where it is absorbed by the atoms and molecules that are present in it. And then this extra absorption will be recorded by ground-based facilities such as the espresso spectrograph. And then by comparing the in to out of transit flux, we are in theory able to detect the extra absorption from the planet itself. Great. This is so successful that to date more than 50 species have been detected in more than 100 exoplanets. And among them, sodium is by far the most successful, especially thanks to the strong sodium doublet in the optical at 5,800 angstrom. And we can see that from this diagram where I'm showing the mass as a function of the orbital period of all the exoplanets where sodium has been analyzed in transmission spectroscopy. However, in all these detections, only 1D canonical stellar models have been used so far to correct for the so-called CLV effect. CLV stands for center to limb variation, and it is a well-known effect that means that the spectral lines varies in the stellar disk in strength and shape. So, because they are forming in increasingly higher layers, going from the disk center to the limb. So, for instance, if we take the solar disk and we point our solar telescope to the disk center, we will observe a certain line profile. This is the sodium D1 line, for example. Then, if we take our telescope and we point it at the edge of the solar disk or limb, and we observe the same line, we will see a completely different line profile that varies in strength and shape. And why is this important in transmission spectroscopy? Because, as you can see from this animation, during the transit, the planet is selectively blocking the light from different parts of the stellar disk, which contribute differently to the final observed stellar line profile. Therefore, the stellar line that we observe is changing during the transit, as we can see from the light blue line in the plot on the right, which represent the ratio of the in-transit to out-of-transit flux of the star, of course. So this effect can be measured on the sun, because the solar surface can be spatially resolved. However, this is not generally the case for the other stars, since they appear as point sources in the sky. Therefore, we need to rely on synthetic stellar spectra to correct for this effect in our transmission spectroscopy data for the sodium D lines in this case. So, as I said, the CLV is observed in the sun, and this is measurements from the Swedish Solar Telescope that I took during my first PhD project. And here we can see how the equivalent width of the sodium D line is changing, going from the disk center to the right to the disk limb to the left. And if we compare these observations to models in 1D LTE, 1D non-LTE, 3D LTE, and 3D non-LTE, what we see is the following. So in 1D, both LTE and non-LTE are underestimating the equivalent width a lot at the limb. Then if we switch to a more realistic three-dimensional atmospheres, but still assuming local thermodynamic equilibrium, we will see something in between. And finally, only using a full 3D non-LTE calculations, we can get a very nice match with the observations, as you can see here. So yeah, the takeaway is that solar CLV of sodium D lines cannot be reproduced by 1D models. And well, I did also a simulated transmission light curve for a Sun-Jupiter system on a edge-on orbit using the star rotator code by Jens. And what I noticed is that using different synthetic spectra, the CLV Rossiter-McLaughlin model will change the shape quite a lot. So it is strongly dependent on the stellar synthetic spectra that we adopt, and therefore it's important to use a model that is as accurate as possible. So, as I said, apparently it seems that modeling in 3D non-LTE is required to correctly reproduce solar observations. And how can we do that? Using a three-dimensional model atmospheres, and the one that I'm using in my work are from the Stagger grid that has been recently extended and refined. And then once that I get the model atmosphere, I put them in a radiative transfer code that compute calculations in non-LTE. The one that I use is Valder, and it's a modified version of Multi3D. And the animation that you see on the right is it's representing several snapshots from the most recent staggered solar simulation, and you can see how the convection pattern is varying in time. So once that I've done all this work for the sun, the next natural step is to go to other stars and to compute 3D non-LTE stellar spectra for the sodium lines in this new stagger grid. And the extent of the grid is shown in this plot where we have the gravity and the surface gravity as a function of the effective temperature, and each slides represent a different metallicity model. So if we overplot on this grid some of the stars that are hosting exoplanets where sodium has been analyzed or even detected, we see that they all lie in this yellow shaded region. So I decided to compute 3D non-LTE stellar spectra only in this region because they are very computationally expensive. And now the next natural step is to apply this spectra to a benchmark hot Jupiter observed with the best facilities that we have currently, which is in the optical is espresso. So when you think about the benchmark hot Jupiter, for sure it comes to your mind the iconic HDO 209458b, which is a giant planet that has been extensively studied with both low and high resolution spectroscopy during the years. And it has a somehow troubled history of sodium detections, non-detections, that I will now briefly summarize. And the questions that I'm trying to answer is the following: if there is actually sodium or not in this atmosphere. So the first detection was at the beginning of 2000 with the Hubble Space Telescope, so low resolution. And then it was confirmed from the ground, then again from space, then from the ground, and then many others until in 2020, Casasayas, Barris, and collaborators, by analyzing high-resolution spectra from ARPS Nord and Carmenes, starting suggesting that maybe the future that they were seeing the sodium wavelengths were coming from the star and not from the planet. So to confirm this hypothesis, they took additional data with espresso, in particular 2 nights of observations with espresso, and in 2021 they were supporting again the non-detection. However, the models were not clear enough, unfortunately, and the detection could not be completely discarded. So what I'm doing now is taking again this espresso data, the same that Casasayas Barris analyzed in 2021, and I'm showing here the transmission spectrum for the sodium D1 and D2 line. And I'm trying to compare these observations with my models from the stagger grid. So if I use 1D LTE model, I see that the amplitude is slightly underestimated at the center, at the wavelength center. If with 1D non-LTE models instead, we see a slightly overestimate of the amplitude. In 3D LTE, we see even a smaller underestimate. And finally, using a 3D non-LTE, we see a very good match with the observations, which unfortunately means that there is no sodium in this planet. And yeah, this is great. I mean, it depends on the perspective. But now with these new models, we can start questioning all the sodium detections in the other exoplanets as well. And I think that with the continuous improvement of the instruments, I think it's important to also use better and better models in order to get more accurate results and to characterize the exoplanets in the correct way. So, to summarize, I have shown that the stellar CLB affects transmission spectra, and actually it varies between different spectral types and also different elements and also different lines in the same element. So it should definitely not be neglected, and it should be corrected in order to get accurate measurements. And in my previous work, I showed that only 3D non-LTE models can actually reproduce the observed CLB in the sun for the sodium D lines, but I also showed the potassium 1 resonance line. And so I know that most of you use 1D models, but don't worry, because I'm computing stellar spectra in 3D non-LTE, and they are coming soon, so stay tuned. And I conclude with my grandparents' HoRSE, because this was the theme of the conference. So thank you for the attention.
Thank you. And this talk will be given by Hayley Beltz from the University of Maryland, and talking about models and theory of exoplanet atmospheres.
Great. Can everyone hear me? Is mic on? Awesome. Thank you for sticking around for the end of the day, for the last talk, especially a theory talk. Appreciate that. That's some bravery. But today I'm going to be talking to you about exoplanet atmospheric modeling and theory, and that's a pretty broad topic, so I've narrowed it down kind of based on the driving questions. I want to go into why do we need 3D models with high-resolution spectroscopy? When do we need them? How do different 3D physical processes affect high-resolution spectroscopy? And I will be talking about magnetic fields, so be emotionally prepared for that. And then I'll conclude by talking about when you should ask your buddy for a 3D model for your data set. Great. So starting off with why do we even need 3D models in the first place, I want to talk about one of my favorite types of observations, which are these phase-resolved Doppler shifts. So in this type of observation, you're able to, at different phases, resolve your data and know what that Doppler shift is. And that's telling you about the atmospheric dynamics of that portion of the planet that's currently facing you or currently going through transit. So on the bottom left, I'm showing you two examples of how this is done in transit, where we've got time on the y-axis and then rest frame velocity on the x-axis. And you'll kind of notice that both of these have sort of a really slanted slope followed by a flattening out. Remember that, that's going to come up later in the talk. And then in the top right, I'm showing you an example for emission spectroscopy, but this time the Doppler shift is on the y-axis and phase is on the x-axis. And so if your planet was one-dimensional, you wouldn't really expect these Doppler shifts to change with time. But as we know, planets are 3D, and so their Doppler shifts are going to change as you look at different parts of the planet. And to complicate this even further, not all species are going to be shifted the same. So on the left, I'm showing you some theoretical predictions of net Doppler shift on the x-axis and time on the y-axis. And you can see that some species have similar profiles that could tell you that these species are probably probing similar parts of the atmosphere, but others, and in this example, TIO sticks out, looks quite different. And that could be due to a number of different things, but could be the fact that maybe your species is dissociating, maybe you don't have a uniform chemical abundance of that species, and maybe you're probing a different part of the atmosphere entirely with that species. And then on the right, I show you an example from data where we see the difference in net Doppler shift from 2 points of in time, and then the line strength on the y-axis. And so from this, you can gather that different species are moving in different directions. Some of them are blue shifted, some of them are red shifted. This is a complicated problem. And so let's get into some of the things that can change our net Doppler shift. And shout out to Arjun Saval, who made this slide. And we can think about basically 3 different categories of things that can change our net Doppler shift. We have parameters related to the orbit, parameters related to the atmospheric dynamics, and then parameters related to chemistry. And so a non-exhausted list of these can be shown here. So in your orbit, maybe your ephemeris is wrong by a little bit. That can change your net Doppler shift. Maybe there's some tidal deformation going on. As far as atmospheric dynamics, where I like to think a lot about, you've got things like Lorentz forces from magnetic effects. You've got things like your equatorial jet, day-to-night winds. And then from the chemistry side, you also have things such as clouds, condensation, photochemical reactions, and your data set probably contains some combination of these different effects in varying degrees. And so it can be difficult to isolate exactly what is driving your net Doppler shift without looking at a 3D model. And speaking of net Doppler shifts, there have been talks this week, both yesterday and tomorrow, so definitely check out these talks to look at some observational examples of this. So when we were looking at spectra as a function of time, in emission, our planetary spectra is going to change as a function of time. So on the top left, I'm showing you some spectra from a planet at varying phases. And depending on the location of your hotspot of your planet, that's going to determine when the flux of your planet is really going to be the highest. And so if you don't account for this, this could bias your retrieval or your analysis. And then on the right, I'm showing you what happens for a single CO line as a function of phase. So the y-axis is showing you line contrast, and then we are color-coded by the phase of the line, or phase of observation. So even though CO is a pretty well-behaved species, we don't expect it to dissociate. It's probably pretty uniformly abundant around the planet. The line strength is going to differ because your line strength is going to be set by your temperature profile as well as your temperature gradients. And it turns out that there's also temporal dependence in transit spectra as well. For hot Jupiters and ultra-hot Jupiters, which is the focus of this talk, these planets can rotate quite significantly during orbit, sometimes over 30 degrees. And you can see an example of this in the top right, where I'm showing 3 different projections of the planet at ingress, mid-transit, and egress. And what you're seeing color-coded is the temperature. And the important bit to take away from this plot is that the planet looks different at these 3 different phases. And if you don't account for that in your spectra, you're not going to necessarily get the highest detection you can. And the way this can show up in spectra is shown in the bottom left from Elsie Lee et al., where we're looking at transmission spectra for a very tiny phase range, but we can see that there's differences among the line strengths, the sort of maximum depth that your line has, and all of these are going to play an effect in your transmission spectra. And there are more talks this week about transmission spectra in high res, so definitely check these out or watch the recordings later. And so maybe at this point you're like, okay, Hayley, I don't want to think about 3D effects. What if I don't phase resolve anything? What if I just shove it all together? Unfortunately, 3D effects are still present in your data. So in 2020, for the first time, we used a 3D atmospheric model to generate high-resolution emission spectra for a hot Jupiter. And then we compared that to CRIRES data. And we additionally compared a suite of nearly 700 1D models as well. And we found that our 3D model, without really any fine-tuning, was able to get a sigma-and-a-half better detection than any of the 1D models. And we concluded that most of this increase in detection significance came from the fact that we were using a 3D temperature profile. Things such as including Doppler shifting and the different chemistry choices we used also slightly increased the the detection significance, but was secondary to the use of a 3D temperature profile. And so this has also been shown in transmission spectra, first by Flowers et al. In 2019, who once again took a GCM, post-processed it to make high-resolution transmission spectra. And so what these 2 plots are showing are detection significance contours, and then the x-axis is the planet rotational velocity, so how fast is the planet rotating, versus the rest frame velocity. And on the left, this plot was created with spectra that did not include Doppler broadening. And if we look at the green star, that corresponds to the expected location of the planet. And we see that on the left, the green star is outside our detection, or our 1 sigma contour. However, on the right, these spectra were generated with Doppler broadening from winds and rotation, and now we see that the star representing the planet lies within our 1 sigma detection. So both emission and transmission data have these 3D effects embedded in them. And so that begs the question of, when do we need to use 3D models? As much as I love them, it's not really computationally feasible to use one for every single high-res paper. I don't think we have enough GCM modelers for that. But I've been talking a little bit about 3D models, and what I mostly mean are what are known as general circulation models. And so these are 3D numerical models that solve fluid dynamic equations that represents gas flowing in an atmosphere. And I show an example of this on the right. Okay, good, it's on the right. As the planet rotates, the background color is showing you the temperature, and you can see arrows showing you the wind directions. And if you watch the GIF, you can see that the temperature and the winds change as a function of longitude and latitude. Very much planets are three-dimensional. And so with a 3D GCM, this will often be coupled with a radiative transfer routine. And different GCMs use different complexity radiative transfer routines, but that's an important part of your GCM. Additionally, GCMs may include different additional physics, such as clouds or hazes, magnetic effects, hydrogen dissociation, and many more. And so thinking about 3D models versus 1D models, I'm not entirely down on 1D models. They are definitely important and helpful. So 3D models have the benefit of being more physically motivated. You're able to capture some 3D effects. And most importantly, in my opinion, you're able to interpret results by linking back to atmospheric dynamics. It can help you understand, why are you getting Doppler shifts? What is this meaning? On the downside, these models take a long time to compute, usually over a month, and that's assuming it doesn't crash beforehand, which happens a lot. And post-processing these 3D models is not trivial to do a 3D radiative transfer. 1D models, on the other hand, although they don't account for 3D physics, it is much more computationally feasible to generate grids of hundreds or thousands of models. And so if your goal is to detect as many species as you can in a particular planet, a 1D model is probably the best way to go, because you're not going to compute hundreds of GCMs. But I warn against using 1D models to interpret atmospheric dynamics, because there's a lot of 3D effects that aren't included. So depending on your data and what your goal is with your analysis, that can kind of help determine whether or not a 3D model is the best choice for you. And so there's a lot of talks later this week about both 1D and 3D models, so definitely check those out as well. And so now we can move into how do 3D physical processes affect high-resolution spectra. So I'm going to be focusing on clouds, limb asymmetries, and magnetic fields. So clouds have a spatial dependence. And on the right, what I'm showing you is a temperature map on top, and then a cloud opacity map on the bottom. And so on the bottom plot, where the areas are white, that's telling you you have clouds. The areas that are dark are cloud-free. And then on the left, I'm showing you from Kamasek et al., different cloud opacity as a function of pressure. And so these different lines corresponds to different parts of the planet. So the dark blue line corresponds to the antistellar point, which is very cold. We would expect clouds there. Great. The light blue line corresponds to the western limb, which also is expected to have clouds for this particular temperature. Now, what's not on this plot is the substellar point, which is too hot for clouds, and the eastern limb. And this matches what we see in the plot in the bottom right, where the substellar point is in the center of the plot. There are no clouds, and then the eastern limb also shows no clouds. So you have this inhomogeneity with your clouds depending on your temperature of your planet. And it's important to consider clouds because there's evidence to suggest that clouds may increase the C/O ratio that you measure. And so since we often want to use C/O ratios to link back to formation mechanisms, we want to think about whether or not clouds could be in our data and could or could not be biasing our results. And so that's all I'm going to say about abundances in chemical species, but check out these talks or talk to these people if you want to learn some more. And so clouds can also affect the net Doppler shifts in emission. So here I'm showing you two different models of two different planets, and we'll start on the bottom left, where the purple line shows you the clear model, and the green line shows you the cloudy model. We've got orbital phase on the x-axis, and I've indicated where secondary eclipse is, and net Doppler shift on the y-axis. And we can see that these are pretty similar for this planet. There's maybe some differences, but probably on order less than a kilometer per second, less than the current sensitivity that we have. But on the right, we've got a model for another planet. Again, orbital phase on the x-axis, net velocity shift on the y. The gray line shows the spectra generated from the planet without any clouds, and then all of the colored lines corresponds to different cloud prescriptions. So it doesn't really matter for this talk what these cloud prescriptions mean exactly, but what is important is that they can really influence the net Doppler shift, sometimes by several kilometers per second. So we see sort of a varying level of effect of clouds on our net Doppler shifts in emission. And they can, of course, affect net Doppler shifts in transmission as well. So here we're looking at Doppler shift on the y-axis, phase on the x-axis, mid-transit is right in the center. So the solid lines correspond to the cloud-free models, and the dashed lines correspond to the cloudy models. And we can see that the cloudy models start off much more strongly blue shifted by over, in this case, several kilometers per second. Definitely something that is in our detectability limits. And so these matter in transmission as well. And I know I've said it a bunch that planets are 3D, but they're also not spherical. On hot and ultra-hot Jupiters, our day side is so much hotter that the scale height is going to be much larger and will spatially extend on the day side compared to the night side. And so that's what's shown here on the plot, where we are looking at two different species, iron on the top, water on the bottom, and you can kind of see the puffed out bit of the atmosphere on the left side of each of these. And so what these blue and red regions correspond to are where the line cores and the continuum is set. And we can see that for iron on the top compared to water on the bottom, that these species are probing very different pressure regimes and areas of the planet. Water has the extra complication of the fact that it's going to become dissociated on the day side, and so that is something that needs to be taken into account. So the same species can have different net Doppler shifts for each limb, which is what we see here. And so limb asymmetries can be caused by multiple mechanisms, including the scale height effect from the atmosphere being much hotter on the day side, chemical gradients, clouds, whether or not you include TIO or VO, and for some species, line blending, if there's not too many lines for the particular species. So here I'm showing you a plot where we've got a bunch of different species on the y-axis, and then the x-axis is showing an asymmetry parameter. And what to know from that is that if you're to the left of that black line, you have a higher concentration of that species on the eastern limb. If you're to the right of that line, you have a higher concentration on the western limb. And we can see that there's quite a bit of scatter between species, and that there's a scatter between the positive ions in pinkish and the negative ions in the sort of teal color. But once we include the scale height effect, these abundances look different. So now, once we include the fact that the atmosphere is not a sphere, we can see that all of our species have preferentially moved to the eastern limb. But there still is some scatter between species and some differences between our positive and negative ions. And so now, to go into magnetic effects, in this case, we're thinking about a dipolar magnetic field. In general, your dipolar magnetic field can damp wind speeds because any kind of ions in your atmosphere don't want to cross magnetic field lines. And so on this plot, we've got temperature on the x-axis and east-west wind speed on the y-axis. And then these different color contours on the background are different magnetic field strengths. So in theory, your magnetic field strength could set an upper limit of how strong your east-west wind speeds could get if your planet has a dipole. And so before I get more into magnetic fields, let's take a step back, because most people don't think about magnetic fields every day because you're more well-adjusted than me. But I like to think about it how on the day side, temperatures are hot enough that we're going to thermally ionize some atmospheric species. And then these ions are going to become embedded into the strong but mostly neutral winds and get blown around the planet. And so since you have moving charges, if we assume some sort of deep-seated magnetic field, a moving charge is going to generate a current and dissipate energy. This is known as ohmic dissipation. And then what I like to focus on, from the charged particles' point of view, as they cross magnetic field lines, they're going to experience a Lorentz force. That's our right-hand rule from physics 1 or 2. And so they will resist, they will not want to cross those field lines. And so we parameterize this Lorentz force as a magnetic drag timescale that varies as a function of temperature and pressure. And so I won't go into the gory details of the timescale, but I'll talk about what that does to our atmosphere. So here I'm showing you temperature plots for various magnetic field strengths, 0 Gauss on the far left, 30 Gauss on the far right, and pressure on the y-axis. So we're near the top of the atmosphere, and if we look at the 0 Gauss case in the top left, we can see that on the day side, we've got some eastward motion. I drew the black lines on there so it'll show up better on these projectors. But on the 30 Gauss case, and all of our magnetic field cases for this higher pressure level, we see that the flow on the day side has changed, and now it's going only in the north-south direction. It's going up and over the poles. And so that's going to produce a different net Doppler shift than the 0 Gauss case. And if we go down one row, so we're going a little bit deeper in the atmosphere, we can see that for the 0.3 Gauss case, we have a little bit of eastward motion, not much, but a little, while the 3 and 30 Gauss case still are only showing that north-south motion. So the magnetic field strength can kind of help determine how deep this magnetic circulation pattern, where we're going up and over the poles, persists in the atmosphere. And so now I'm going to show you some plots from a work I have in progress. I have the reviewer report, I just need to do it. But in this paper, I looked at 3 different ultra-hot Jupiters, ran both magnetic and non-magnetic models, and calculated high-resolution emission and transmission spectra. So in both these plots, the non-magnetic case is at the top, and on the bottom is the case with magnetism. And so for emission, what we see is that we see different shifts in velocity before and after secondary eclipse between our 2 models. There also seems to be maybe more variation between planets. I only have 3 data points, but I wouldn't be the first astronomer to extrapolate based on 3 data points. But in transmission, we see a sort of interesting shape. In our magnetic models, in that bottom right panel, we see a really steep slope followed by a flattening out, while the drag-free models instead just kind of become more slightly blue-shifted with time. And so from this work, there are some initial trends that seem to be stronger in transmission, but there is a dependence on planet choice, wavelength, opacity source, and so there's not necessarily a smoking gun yet. I don't have too much time to get into this, so feel free to ask me about it later, but a current open question is the fact that our GCMs are having trouble matching some of the magnitudes of these observed net Doppler shift. So these are 2 different GCMs, both trying to fit the same Ehrenreich 2020 data set. The GCM on the left includes clouds, the GCM on the right includes magnetic fields. And so neither of these GCMs are able to reach that negative 12.5 kilometers per second, but I would maybe argue that the magnetic case on the far right shows a similar shape to the Ehrenreich data, with that strong slant followed by a flattening out. So finally, I want to conclude by telling you about when you should ask your buddy for a 3D GCM. So if you have phase-resolved Doppler shifts that you would like to interpret and discuss atmospheric dynamics in, a 3D GCM is really helpful for this. If you have a planet that might have a really strong magnetic field, so ultra-hot Jupiters or the hot Jupiters, that might be a good case for a 3D model, as well as planets that are going to be non-uniformly cloudy, particularly in transmission. Also, if your planet maybe has strong limb asymmetries, and finally, if you're willing to wait at least 1 to 2 months, or even ask earlier would be lovely. So with that, I hope I've convinced you that 3D models are important and can be helpful in high-resolution spectroscopy. And with that, I can take any questions. Thank you.